questions and inquiry about your PhD work. Okay, thanks. Can you start, please?
Yes, so everybody can hear me? Hello?
Yes.
Okay, so I will start now. Just a minute, I have. I can share. So I know how to share. So it's like
this upper.
this one?
Nope.
Oh. Okay. So hi everyone. So can you see my presentation, the first page?
Yes.
Okay, so I will start now. Hello everyone, I'm Saqib Hussain and this is my PhD defense. And Elisabete Pino is my supervisor. And I will present my work of PhD about cosmic rays, propagation in cluster of galaxies, and the production of gamma rays and neutrinos. The main motivation of our work is to study the high energy fluxes. As you can see from this figure, that the high energy flux of gamma rays, neutrinos, and cosmic rays is comparable. If they are comparable, they may have common origin. If they have common origin, it means they can be produced by a single class of astrophysical sources, maybe by AGNs or star-forming galaxies, or more importantly by the cluster of galaxies, combinedly by the AGNs or star formation inside cluster of galaxies. Cluster of galaxies are very attractive candidate because they have a large size and magnetic field strength. So due to their large size and magnetic field strength, they can confine cosmic rays of very high energy up to 10 to the power 17 electron volt and can produce a high energy neutrinos and gamma rays due to their interaction in the intercluster medium. And finally, we will make some particle emission or space distribution constraint for the gamma rays or neutrino observatories. So the outline of my work will be, first I explore the 3D MHD simulation of the intercluster medium and intergalactic medium up to redshift 5. And then we use that background to study the cosmic ray propagation and cosmic ray acceleration in that background. And further, we calculate the gamma ray flux and neutrino flux from that background due to cosmic ray interactions. And we compare our results with the already observed neutrino observations by the IceCube and Fermi-Lot by the diffuse gamma ray observations. And then we also compare our results with the sensitivity curve of LASSO and forthcoming CTA as well. So this is the methodology how I proceed. So first we explore the 3D MHD simulations. And from that simulation, we extract the properties of the clusters like magnetic field, gas density, and temperature. And we also study the cosmic microwave background or different photon field like extragalactic background light or radio background light, or also implement the Bremsstrahlung photon field of the intercluster medium. And using that photon field, first we calculate the mean free path of different cosmic ray interactions, and we implement these cosmic ray interaction to study and the cosmic ray propagation. Actually, we use CR-Propa code to study the propagation of cosmic rays after implementing all the relevant interactions. And finally, we calculate or derive the flux of cosmic rays, gamma rays, and neutrinos. So this is the summary of background MHD simulations, which we use. That's actually MHD simulation performed by a gadget code. It's actually SPH, smooth particle hydrodynamics simulation. And here you can see the total volume of the simulation at redshift is equal to 0. And we have different slices of these background simulation up to redshift 5. And the maximum resolution of the background simulation is around 10 kiloparsec in the center of the structure, like clusters, and it increases if you move away from the clusters. And here in the middle panel, I'm showing 1/8 part of the total simulation. And here you can see this is the magnetic field distribution, and you can see the filaments, voids, and the densest part correspond to the clusters. And in this is the temperature distribution of the same 1/8 part. And so these last column actually show one of the cluster of mass 10 to the power 14.5 solar masses, the magnetic field distribution, temperature, and density distribution. Here you can see these quantities, the distribution of these quantities are not spherically symmetric, and this deviation from the symmetry may affect the emission pattern of gamma rays, neutrinos, or cosmic rays as well. This simulation we are using, it's actually performed by Dolag in 2005. They thoroughly compared with the observations. Here you can see we are comparing the X-ray surface brightness of 3 clusters of Coma and these 2 clusters, and you can see their results are roughly matching with the average temperature measured from the simulations. You can see by the gray bands here, and this is for low mass cluster, and upper one is for massive clusters. And the right panel actually show the robustness of the simulation. So which show actually the projected gas density map around these 3 structures. And you can see the contrast in the density between voids and the densest part of the simulation, like cluster of galaxies. So as we extract the properties from the MHD simulation, here I'm just showing some the general trend of 4 clusters of similar mass, 10 to the power 15. So these are volume average profile with respect to dark matter, number density, gas mass, magnetic field, temperature, and over density. You can see in case of magnetic field over density, it will decrease as you move toward the outskirt. That's obvious results. In case of temperature, you can see especially in these 2 clusters, the temperature distribution, even in case of volume average profile, it behaves differently. Suppose in this case, like in these 2 clusters, the temperature is a bit low in the center and it's high in the outskirt, which this temperature variation are the indication of shocks. Further, I'm also showing the magnetic field profiles of 3 clusters of different masses. So it's also by bit obvious results that for massive clusters, the magnetic field strength will be more as compared to the less massive one, and it decreased toward the outskirts. This is also volume average profile. And we also compare our results with the density profile of one of the clusters of mass 10 to the power 15 solar masses with the beta model, which actually the beta models actually define the density of the cluster. It's a radial profile, which by assuming that the isothermal distribution of the total matter, dark and luminous matter, and we compare this our density distribution with the beta model. As you can see, this is again the volume average profile, like of you average over a concentric shell of radius of different radii up to toward the outskirt. As you can see, the density decreasing toward the outskirt. That's the same for both cases, but in our case, in their case, there's a clear difference in the density distribution in the outskirt after, you can say, 800 kiloparsec and above. And that deviation may also create a difference in the emission pattern if you use a beta model. So the emission flux may be different if you use than the MHD simulation being used. So this is then we also calculate the number density, or you can say better way to say the number of cluster per unit mass interval, and this way we will use to calculate the total flux from the entire range of the clusters or for different mass intervals. As we estimated this density, the number of cluster per mass interval for different redshifts. These are all the number of snapshots we have of the background simulation, and then we use that quantity to calculate the entire flux, the total flux of from the entire population. So having said that, so that's the background simulation I just overviewed or summarized, and then we use that background simulation and study the propagation of the cosmic rays inside these structures. So the mass range of the clusters we have from the background simulation is 10 to the power 12 to 10 to the power 15.5 solar masses, and so we inject cosmic rays in the center and in the outskirt at different injection points, like at 300 kiloparsec and 1 megaparsec inside the cluster, by assuming that the cosmic ray sources might be present at different points in the cluster, in the outskirt or a little bit away from the center. And so, and then we inject the cosmic rays. For neutrinos, we inject the cosmic ray of energy range 10 to the power 14 to 10 to the power 19 electron volt, because our energy range of interest, in case of neutrinos, we are interested in the diffuse neutrino background above energy 10 to the power 14 electron volt. That's why we choose this energy range. So we inject that cosmic rays and we collect and we implement all the relevant interaction of the cosmic rays with the gas density, with different photon fields, or they are being tracked by the magnetic field. And so we implement the interaction with cosmic microwave background, galactic background light, or radio background, or Bremsstrahlung photon field as well. And after implementing, so we propagate the cosmic rays in the cluster and calculate at the edge. And from the edge of the cluster, so in case of neutrinos, so then we propagate these neutrinos from edge of the cluster up to the Earth. But in case of neutrinos, you don't need to consider any attenuation effect due to EBL or any other photon field, because they are not going to interact. And also you don't need to consider the intergalactic magnetic field in case of neutrinos. So this is our cosmic ray simulation setup. To study the propagation of cosmic rays, one can use the approach, the simple equation of motion approach. So in this approach, so you can use any arbitrary magnetic field configuration. You don't need to assume any diffusion tensor. But this approach is very computationally very expensive. If the cosmic ray energy is below 10 to the power 15 electron volt or so, and we can also use this the transport equation approach by using stochastic diffusion equation. So in this approach gave a quite approximate result, but the main assumption one has to make is to assume the diffusion tensor to study the propagation of the cosmic rays, and that's to implement the quasi-linear theory actually. So we study the propagation here. So first we estimate the diffusion of cosmic rays. Here we are just showing the diffusion of two cosmic rays of different energy, 10 to the power 16 and 10 to the power 17.5 electron volt. You can see that the trajectory of cosmic rays, of low energy cosmic rays, let's say here 10 to the power 16 electron volt, it seems more diffusive. You can see by the thick line, and as more interacting with the medium as well. And for a high energy cosmic rays, for 10 to the power 17.5 electron volt, it's less diffusive, or you can say ballistic, the trajectory of cosmic rays. So like here we estimate calculate the Larmor radius for energy of cosmic ray 10 to the power 17. As you can see, it's like 100 parsec. If the energy is even higher, then Larmor radius will be even larger, so the trajectory will be less diffusive for high energy cosmic ray. So as we implement, so in our using the propagation of cosmic ray, we study by the stochastic diffusion equation approach, because the equation of motion approach is computationally very expensive. So we use that approach. So actually implement the quasi-linear theory. Here I'm showing the result for cosmic ray flux for one of the cluster of 10 to the power 15 solar masses for two different diffusion value of the diffusion parameter. For 0.1 and 0.5, you can see for a large perpendicular diffusion coefficient is equal to 0.5, it's the cosmic rays can escape easily, or you find a more the flux of a cosmic rays is a bit higher if you assume that the diffusion coefficient is a bit larger, then the perpendicular diffusion coefficient is a bit larger than the parallel one, and it's opposite if you say that the perpendicular is smaller than the parallel. So this test or assumptions are these are just to we choose these values to implement so that we can implement quasi-linear theory, or if the cosmic ray energy is higher than 10 to the power 16 or so, this assumption is not important at all. This assumption will washed out, as you can see. If the energy is higher, so the flux for both cases is same. So as I discussed which approach we use and why we choose the diffusion equation approach. So and then we also consider the relevant cosmic ray interactions in that medium. So these are the possible cosmic ray interactions. They can interact with the atmospheric nucleus and produce pions, and these pions can further decay to neutrinos or gamma rays as well, and these gamma rays can further cascade. But they can also interact with the background photon field and produce the pions as well, and they further decay to neutrinos and gamma rays as well. And this is actually the cascade of gamma rays to pair production and further gamma rays as well. So as we are using different photon field like Bremsstrahlung, local Bremsstrahlung photon field and extragalactic background light, here we show that how these photon field, or in which energy range these photon fields are comparable or dominant. You can see here we're plotting or comparing two ABL model with Bremsstrahlung photon field of two clusters. So these are two different approaches to calculate the ABL model. The first one is completely observationally driven, and the second one is based on the semi-analytical models. But you can see their energy density is same for both cases, or at least overlapping in the main region, in the infrared and optical region. And in case of Bremsstrahlung photon field, we calculate the Bremsstrahlung photon field very near the center, in this radius, within this radius, and in the outskirt. So Bremsstrahlung photon field is more dominant in the center. And also we plot here for two clusters of different masses. If the cluster mass is less than 10 to the power 14, we found that the Bremsstrahlung photon field is not important at all. And here it is important only in the X-ray region, only for very massive clusters. So after implementing that, these photon fields, and we study the propagation of cosmic rays here. So I'm presenting or showing that how the trajectory length while propagation of cosmic rays of different energy is comparable with the mean free path. Here, these quantities are being calculated for a cluster of mass 10 to the power 15 solar masses, and the flux is calculated at the edge of the cluster. So these are the mean free path of different cosmic ray interactions. You can see that the main interaction which is important for low energy cosmic rays, if energy is less than 10 to the power 17, is proton-proton interaction. And if the energy is greater than that, then the photopion production with CMB and EBL, they are also important, but CMB is more important. We also estimated if the photopion production in case of CMB might be important, but as the mean free path for inverse photopion in case of Bremsstrahlung and photopion in case of Bremsstrahlung, the mean free path is greater than the Hubble horizon. And secondly, as you can see here, the trajectory of the cosmic rays, the trajectory is actually the total distance a cosmic ray covered before its escape from a cluster. So for each energy bin, for different energy bins, actually for the entire range, we have number of events or the number of cosmic rays whose trajectory length is larger or even larger than the mean free path, which indicate that these interactions are inevitable, especially these three, to produce high energy neutrinos and gamma rays. This is also the electromagnetic cascade processes. I'm showing the mean free path of pair production and double pair production, inverse Compton scattering, and triple pair production. In case of, as you can see by the dashed line, that the pair production or inverse Compton scattering is more dominant for the case of CMB, and it's least dominant for the case of cluster or Bremsstrahlung photon field. So finally, after implementing all these interactions and the background, using the background MIT simulation, we calculate the flux of cosmic rays and neutrinos. Here I'm showing the flux from cosmic rays and neutrinos from individual clusters of different masses. So in case of heavy clusters, if a cluster mass is heavy, and we also studied for different injection point as well. So if you inject a cosmic rays in the center, so it will be difficult for them to escape due to high magnetic field strength and high density, and so their flux will be lower if you inject in the center, as you can see by the solid lines, for all the solid line like red, green, or blue. And if you inject in the outskirt, then they can escape easily, so their flux is higher. And similar for the case of 300 kiloparsec. In case of neutrinos, so for the central injection point, there will be more interactions, and consequently, there will be more secondary particle production. Like neutrinos, you can see by the solid lines, the red solid curve for this mass, that the neutrino flux is much heavier if you inject in the outskirt or for the less massive cluster as well. So the simple conclusion that the massive cluster produce more neutrinos than the less massive one. So, and then as we studied the cosmic ray propagation and the neutrino flux for cluster of different masses at different redshift, so we calculate the total flux for the entire redshift and mass range. So we use this equation to calculate the total flux. So this quantity here is E square dn dot over, this is a flux, and dn over dm is the number of cluster per in unit mass per mass interval, and we integrating over the whole mass range and whole redshift range. And this phi function is actually tell the source evolution, cosmic ray source evolution. I will explain this later, and this dl is the luminosity distance. And so in this figure, you can see I compare our results with the IceCube data points, and we also compare with Fang and Olinto, because they also did the similar study and estimated the flux with the same redshift range for neutrinos. So our flux for a spectral index, cosmic ray spectral index 1.5 and cutoff energy 5 in 10 to the power 16 electron volt, the flux are quite matching with the IceCube data points, and our results and the total flux is also matching with the Fang and Olinto as well. But in our case, the major contribution came from the nearby cluster, z lesser or equal to 0.3, and in their case, the major contribution came from 0.3 to 1. And this difference is not that much, as you can see by the dotted line in their case, and in our case, is by a factor of 2. And the reason may be the reason of the difference, because they consider the spherical symmetric radial profiles to probe the density and magnetic field distribution of the clusters, and also the difference in the low mass range from 10 to the power 12 to 10 to the power 14 solar mass cluster, the distribution of the clusters, these are different in our case and their case. So these are maybe the reason for the difference. And then we also calculate the total flux for different mass intervals for the entire mass range, but for spectral index 2. But in this case, our results are not matching that much, and they are matching with the Fang and Olinto as well, but not with the ice cube for the case of spectral index. And it is the major contribution again come from this mass interval 10 to the power 14 to 10 to the power 15 solar masses, and it is same for both cases, for Fang and Olinto and for our case as well. So further here, I'm showing the neutrino flux, and we try different total neutrino flux to fit or to match with the ice cube data. We plot for different spectral index. As you can see, for all the values, we are considering cutoff energy 5×10 to the power 17 electron volt, and the flux is matching even in case of 1.5 spectral index. It's overshooting the ice cube data points, even for 1.9 as well. But they are matching with the ice cube data points above energy 10 to the power 14 to 10 to the power 16. And here I'm plotting, I show the flux for different cutoff energy of cosmic rays, but for spectral index 2. And for spectral index 2, the results are not matching that much with the ice cube data points. So our results are quite dependent on what spectral index we choose to inject cosmic rays and cutoff energy we use. And then finally, this is so here the total flux of neutrinos, but here I include the source evolution effects. So by assuming that if the cosmic ray source evolution, if the cosmic ray sources have the same evolution as AGNs, or they follow the star formation rate, then due to the large input of cosmic rays due to these sources, which follow these functions, and these functions are observationally driven, both cases, you can see in these references. So they can enhance the flux of scan due to the large input of cosmic rays, due to the presence of these sources. They can increase the flux of neutrinos and gamma rays as well. Here we are showing just the flux of neutrinos for a spectral index 2 and cutoff energy 10 to the power 17.5. So you can see there is a difference you can see by solid lines, brown, blue, and green. So the flux, if we include these functions, our flux of neutrinos increased by a factor 2 or 3, and so our results are now matching well with the ice cube data points. And yes. And as I presented the total neutrino flux and comparison with the ice cube data points, now I will proceed how we estimate the total gamma ray flux. So in case of neutrinos, we were interested in energy range 10 to the power 14 and above. And in case of gamma rays, we are interested in energy range 10 to the power 10 electron volt and above. So that's why we injected this cosmic ray energy range. And the first part, in case of for gamma rays, is similar to neutrinos. Like you implement all the interactions and inject the cosmic rays at different injection point as well, and calculate them at the edge of the cluster. And then from edge of the clusters, you propagate them up to the Earth. In case of gamma rays, we implement all the cascading processes due to CMB, EBL, or radio background. And in case of intergalactic magnetic field, we didn't implement or didn't consider its effect. First of all, it's highly uncertain, as there are many models which predict the different results, as you can see in these references. And we don't expect any major effect in the gamma ray flux at energy above 10 to the power 10 electron volt. So this is the gamma ray flux from individual clusters of different masses. So these results are similar to neutrinos. The massive cluster will produce more gamma rays, and if you inject cosmic rays in the outskirt, then there will be less gamma ray production due to low density and low magnetic field strength. And similarly, if you inject in the center, there will be more gamma ray production. So for the propagation of gamma rays from a cluster edge or cluster boundary to the Earth or to the observer by different redshifts, so we suppose a uniform distribution of sources, and to see how much our assumptions depend on this uniform distribution, we also calculate the random realization of the sources, the number of sources within the same different redshift, within the similar redshift intervals, and calculate the gamma ray flux for different redshift ranges, and you can see the effect, or you can see the flux for different redshift intervals are same, so that justify our assumption of uniform distribution of sources, and that's also by the observationally driven that the sources of cosmic rays is uniformly distributed. And then as we studying the propagation of cosmic rays for different redshifts, the EBL attenuation effect is more dominant over for the high redshift range. And here we see for two high redshift intervals, and we plot the flux for these redshift interval, assuming 3 different extragalactic background light models. As you can see, for all 3 models, the results are the similar, but in case of Strecker et al., there is a little bit more attenuation or suppression, because I'm using the upper limit of this model, because they give upper and lower limit both. So if you use the average or out, then your flux will be the same. So, and finally, we estimate the total flux of gamma rays from the entire population of the clusters in the whole redshift range. So this is, the equation is the same we use to calculate the total neutrino flux. There's only difference of factor f of m, and this factor I will explain later. Here I'm showing the effect on the total flux due to the source evolution as well. You can see the major contribution again come from the nearby cluster up to redshift 0.3, and these source evolution can enhance the flux by a factor of 2 or even less. And we are comparing our flux, total flux, with the diffuse gamma ray background observed by Fermi lot. As you can see, our flux is matching with the Fermi lot data points above energy 10 to the power 5 into 10 to the power 11 electron volt or so. And even higher if we consider the source evolution effect. As in the case of neutrinos, we also estimated the contribution from different mass intervals. So to estimate which one produce the most gamma rays. So here you can see the major effects, or the main contribution came from of cluster of mass 10 to the power 14 or above up to 10 to the power 15, and for a cluster of mass 10 to the power 14 to 10 to the power 13. These intervals may be confusing. So this is a major contributor mass interval, and it's overlapping with neutrino as well, but it's little bit different as well, because in neutrinos the major contribution came from 10 to the power 14 and above, and here the major contribution come from 10 to the power 13 to 10 to the power 15 solar masses. And we compare our results with Nishewaki et al., because they estimated the total gamma ray flux for clusters like coma clusters. And okay, so they're not considering the whole mass range, or that's why their flux are a bit lower than ours. But in case of the total flux we estimated for the mass range 10 to the power 15 and above, their flux is matching with that mass range. So and then so gamma ray flux from cluster, we estimated the total gamma ray flux as we already showed, but we compare our results with the different studies, as they also estimated the total gamma ray flux from the clusters. So in case of Neshevaki et al., as we already explained, they estimated only for clusters like Gama. In case of Zendenel, they estimated the flux for clusters up to redshift 0.2, and so their flux is, and they didn't account for the mass range above 10 to, below 10 to the power 13. And these two lines in magenta, in this case, they consider that up to redshift 2, all the clusters or sources are radio loud. And in case of a dashed line, they consider all the sources are, sorry, the 30% of the sources only are radio loud. And in case of Murase et al., they estimated the flux for cluster of mass about 10 to the power 14 and above. So, and you can see there, in all cases, their flux is much lower than ours for energy above 10 to the power 5 into 10 to the power 11, and by a factor of 5 or even more. And so, and then, so their flux is even higher. So as we are using non-radiative MHD simulation, so we are not considering any AGN feedback or star formation in the structures. So if we consider that, so then the density of the background region will reduce. So if density will reduce, then there will be less cosmic interaction and consequently less secondary particle production. So so our simulation is not including those effects. So we consider those effects by following this this article, and so by following this article by a factor f of m, by a mass factor depending on the mass of the clusters, and if we consider that our flux decreased by a factor 2, but it's still higher than all the results, but still matching with the diffuse gamma ray flux, Fermi lot above energy 5 into 10 to the power 11, and so. So finally, so I'm showing the gamma ray flux for the entire parametric range, the cutoff energy of cosmic rays, and different spectral index, which we use 1.5 to 2.5. And we compare our results with the sensitivity curves of different observatories, already working LOSO and HAWK, and forthcoming CTA observatory. So, and this whole parametric range is shown by the pink band. So, and this is plotted for the whole redshift range. You can see the sensitivity curve for different experiments. The sensitivity curve for different experiments is comparable or even higher than the flux we obtained. So, which is an indication that these observatories might be able to observe the high energy gamma rays from cluster of galaxies in the future. So finally, I will show the last slide. So as we estimated the total contribution from cluster of galaxies, shown by a thick line, and compare with the sensitivity curve, and here we also plotted the contribution from different individual sources, from blazar, from AGNs, or from star-forming galaxies. So you can see up to energy 10 to the power 5 into 10 to the power 11 or so, the contribution from the individual sources is they're completely producing their flux is matching well with the Fermi lot data points. And in case of clusters, the contribution for the low energy gamma rays lower than 10 to the power 11 is not pronounced at all, and it's majorly contribute in the high energy gamma ray flux, the cluster population. So, and it's also higher than the sensitivity curve. So let's hope it can be observed by the future observatories or even the observatory which is already working LASSO or HAWK. So, so this is the summary and conclusion of my work. So we estimated the flux of neutrinos and gamma rays from the whole population of the clusters. So we use a very detailed method combining cosmological MHD simulation with Monte Carlo simulations of test particles and study the propagation of cosmic rays, considering all relevant cosmic ray interaction in the intercluster medium. We also consider the gamma ray cascading effect on the gamma ray attenuation. And so we found that the most important channel to produce high energy photons and neutrinos inside the clusters is proton-proton interaction and cosmic ray interaction with the CMB. Other processes are also important like CMB, but these are the most important ones. So our major conclusions are that neutrino flux from clusters is comparable with observation of ice cube, especially between this energy range, or the future neutrino observatory might be able to observe the high energy neutrino flux from cluster of galaxies. And in case of gamma rays, so cluster can contribute up to 100% the diffusion of 100 GeV observed by Fermi lot. So, and I will finish with this final comment that the result might be confirmed by gamma rays observatories such as LASSO and upcoming CTA from the cluster of galaxies, and by the future neutrino observatories for high energy neutrinos from cluster of galaxies. And thank you.
Thanks, Saqib. And so now we can start with the inquiry. And it's a tradition in our institution that we start inviting members of the board from the largest distance institution down to the closest, to the nearest ones, right? So our examination board is constituted by Professor Kohta Murase from Pennsylvania State University, by Rafael Alves Batista from Universidade Autônoma de Madrid, Ulisses Barres de Almeida from CBPF institution in Rio, and Professor Gastão Lima Neto and Professor Reinaldo Santos Lima from IAG.USP. So I would like to start by inviting Kohta Murase to make your questions. So please go ahead.
Okay, so thank you very much. The nice presentation. And I have a couple of questions. Okay, so the first, did you compare the mass function that you obtained from simulation with the mass function studied in the literature? So actually, apparently, in my understanding, the evolution is effective evolution looks weaker than the previous literature. So can you show the plot of dn over dm as for the different redshift, if you possible?
No, I don't know. I didn't understand actually your question because.
Oh, okay. Mass function, first time mass function. Actually, can you show the plot of the dn over dm now? So is it possible? The mass functions actually. Did you check the? My question is that the mass functions that you obtain the simulation is important, right? To calculate the diffuse neutron flux, the cluster mass function, dn over dm. So basically the number of clusters as a function of the cluster mass, right?
You are saying, can I show the dn over dm?
Yeah. So have you? My question is, have you checked that the DNOBM is used in the simulation with mass functions using the literature, because the dark matter, basically the mass function was very studied in details using the n-body simulation, right? As you know that higher mass clusters actually found at lower redshift, and the lower mass clusters actually have more are found in the higher redshift.
Yeah. Yes.
And then
Saqib, please, Saqib, show him again the mass function distribution that we got out from the simulations.
Yeah, just let me present again. So the can you see? Yeah. Mm-hmm. Yeah, this one?
Yes. Yeah, because the reason why is that as far as I studied, actually, as far as I know, if you look at the cluster mass function studied in the n-body simulations, for example, and in this case, you have you still have a lot of the clusters.
Yeah. Okay. So, okay. First of all, the massive clusters, you will not find. Okay, and in the low redshift, you will find more massive clusters.
Yeah, but
the high redshift.
Lower mass. Actually, if you go to the lower mass, actually, then in the high redshift, actually, you find more, and then actually, this is, but still is actually the number of clusters you found at the higher redshift still is looks much lower, smaller than the number of clusters.
So here, first of all, there are many lines. So you can see these are the low redshift. Sorry, the low mass clusters. So
but still,
at redshift like this or this, so you have like, you can see the main abundance of clusters is like in this range from 10 to the power like 13.5 to 14.5, let's say. So that's the main abundance you will find at low redshift, like z equals 0.1 or even 0.2.
Yeah.
So you can see by this hump or something.
So
but if the cluster mass is higher than 10 to the power 15, so that's not much at any redshift. Okay, you will find more on the low redshift, but still, in the high redshift, let's say at 1.5 or 5.0, you don't find any clusters of this mass.
Okay. Did you try to compare this mass function with mass function which is studied in the literature? Like hollow mass function is very studied in quantitatively using the n-body simulations. The reason why I asked this question is as follows. Because you show the gamma reflex, the gamma ray background. So but as far as I look, because your gamma ray background is very flat, even above 100 GeV. But I think that several people actually study the accelerated gamma ray background, taking this into account the mass function of the galaxy clusters. But still, is actually you have a kind of the cutoff around the 100 GeVs, and actually your curve is flatter than this curve. So that is why I'm actually wondering the question that if you compare these mass functions, the results from the n-body simulations, and have you compared your results with? Can you explain why your accelerated gamma ray background flux curve is much flatter than the previous results?
So in case of comparison, I can say, so we compare the density of the number of clusters per mass interval, like with different in the literature. So that was quite comparable. Like as you can see at mass 10 to the power 15 or like 5 into 10 to the power 14. So the density from the simulation and from the different literature, you find around 10 to the power -6 or so. So that's what we also got from the background simulation, and in case of 10 to the power 14 as well. But if the cluster mass is lower than that, so then I don't know if it may be my mistake. I didn't find anything in the literature where they specify the density. Okay, usually they comment like there may be like more cluster with the lower mass and they may contribute more, but the specific density, I don't know. I cannot like say exactly if somebody like exactly say something about that.
Can I make an extra comment on this, completing what Saqib said? The fact that, okay, N-body simulations of cluster distribution, cosmological N-body simulations, do not take into account the background the background interactions between the particles, the gravitational particles that are galaxies, with the background gas. So here we have these MADD simulations, cosmological simulations, that do account for these interactions as well. And this probably provides corrections towards the distribution that are not detected in pure N-body simulations, right? Because N-body simulations only account for gravity forces and neglect the presence of the background gas. So we found out very important to use these MADD simulations, to employ MADD simulations to have this full description, as well as to have a good description for the self-consistent description for the background magnetic fields as well. But I'm not saying that this is the main agent that may indicate these differences, but it's a possibility as well.
Yeah, I think that I'm kind of wondering that because it doesn't have to be the simulation result. Actually, the galaxy cluster is measured. Basically, mass function is also studied from the galaxy observation itself, right? And then people actually calculate the gamma background using this. One can use the mass functions, based on the observations, right? And then still, I think the spectrum, the X-ray gamma background is still, as far as I understand, actually it has some cutoff around 100 GeV. Then you have a kind of shoulder-like structure. But in your final results of the X-ray gamma background, actually it's quite flat, even above 100 GeV. So then, actually, if you have an explanation, that be good. But the naive I just wonder is that effective evolution is somehow weaker than this effect. But if you have any other expressions, actually, I don't appreciate, because I'm kind of wondering why the EGB spectrum is quite different. Do you have you actually studied? No, not yet. Actually.
No, yeah, not yet. Okay, so we calculate, you can say the density of the cluster per mass interval and use that density to calculate the entire the total flux.
Okay.
Yeah, this definitely is a good point that should be further explored. Definitely.
Okay. Other questions which could be important that when you compute the neutrino production, the gamma production, cosmic ray nuclei, have you actually taken into account the infrared background actually produced by the individual galaxies? Why did you only consider the EBR only? Because galaxy clusters has the galaxies as members, right? And then they also provide the optical infrared photons. As a result, inside the galaxy clusters, infrared optical background is kind of enhanced compared to the EBR, and then it can actually affect the disintegration of nuclei within the clusters. And then have you considered this? When I look at the presentation, it does not seem that you included this additional photon fields. But why did you ignore these photon fields from the individual galaxies?
Okay, so I didn't consider that photon field.
Do you have any specific reason, just for simplicity?
Actually, no. So the reason, maybe is like they are not okay. So I didn't study that, so I cannot say a specific reason. Okay, I can say like they may not be important, so but we haven't checked yet. Yes.
Oh, okay. Actually, I can say that this is actually can be important, and then they actually affect because of photo disintegration. Actually, it can be affected by the including this additional freeze, and also in principle this can affect the gamma ray cascade. And then did you consider that you actually compute the gamma ray cascade only outside the galaxies, the galaxy clusters? Did you consider the cascade inside the galaxy clusters?
Inside, yes, we consider inside.
Okay. But in that case, of course, if you include the optical additional photon fields, this causes additional cascade in principle. This actually
we try to implement we implement the Bremsstrahlung photon field.
Yeah.
So that was not important at all due to the
Right.
as you already see the main tree path. Okay, so we didn't go to the lower energy. So yeah.
Yeah, okay. I think that might be good to include these photon fields, especially it will affect actually the phase disintegration nuclei. And then that actually is maybe interesting. Another question I have is that when you actually show the detectability of the exterior gamma ray background, but you show the sensitivity curves of the CTA and other detectors, but I'm a bit confused because the CTA is actually has some usually doesn't have a large field of view, and it's very difficult to measure the exterior gamma ray background. And this is also challenging even for the Hawk and the Russell, right? Because they actually they have to cut the cosmic. They have a lot of the cosmic backgrounds. And then in order to study the X-ray gamma ray background, which is actually the more isotropic gamma ray background, they can measure the galactic background is actually the more easily because you can actually use the anisotropic information. But in the case of the isotropic background, this actually where you have to. It's not so straightforward. And as far as I know, I have not seen any sensitivity. Of the kind of established sensitivity for the X-ray gamma ray background for the Hawk and the Russell and CTAs. What do you think?
Okay, so first of all, these sensitivity curves they plotted for the extragalactic background or the gamma ray background, which they may observe like in the CTA book. So,
but they are usually good for the point source or some extended sources, but not the total the diffuse sky, right? Isotropic gamma ray background is actually it's not so easy. Usually you cannot simply estimate the sensitivity from the point source with extended sensitivities, right? I think that still we are not sure about the background sensitivity. Have you found any difference from these diffuse gamma ray background sensitivity curves? Isotropic diffuse gamma ray background.
Can you repeat your question, the last part, because there is some background noise. So
sorry.
In my part, not in yours. So.
Oh, okay. So the question is that how do you compute the gamma ray background sensitivities or the CTA? Because CTA is actually good for the point sources, and then right, and then it's not so easy to measure the isotropic diffuse gamma ray background. So how do you estimate the sensitivity? How do you plot the sensitivity curve?
Okay, so I would say they like already calculated for the gamma ray background. They might be able to observe so I actually exactly plot what they plotted. So in I don't know if you know in the CTA book. So and the gamma ray background, they might be able to observe due to, it can be produced that high energy gamma rays it can be anywhere. So CTA gave you can say the general sensitivity for the diffuse gamma ray background for CTA south and north.
Why is there? Because CTA has only small field of view, right? And it's not the all sky, right?
I think they plotted for the large field of view as well. I don't know if you see that 8th chapter of their book.
I'm actually really.
They actually, I don't know, it's maybe extrapolation, of course. They plotted for the large viewpoint, and this is what they compare with Hawk as well.
Usually they provide the point source sensitivity, and then even the Hawk actually it's a bit tricky to measure the isotropic diffuse gamma ray background. Probably it's better to check their sensitivity curves carefully, and because it's really tricky to do this. Actually, it's actually even for the Hawk and the rest of actually it has to care. They have to care about the background of the coming from cosmic rays, and these are actually the more challenging than the measurements of the point sources, because usually I highly recommend the CTA case. Actually, that I'm not sure because I'm also belong to the CTA, and I have never seen. I have never seen such a plot.
Can I make two comments on your questions and completing the answers by Saqib? With regard to CTA, yes, you are right. We are aware because we also belong to CTA collaboration, as you know, and we are aware that actually this is tricky. But in order to have a comparison or a way to compare with the sensitivity curves of the experiments, we got this one that was, they got this one in the largest possible field of view. So in spite of the fact that it might be associated to individual sources or extended sources, it at least gives us, a comparison or a way of compare with the experiments. But yes, in this sense, you are right that we should at least try to make some estimate on what might be the entirely diffusive counterpart of the sensitivity curve. Yes, this is a tricky point, and yes, it's something that we may further explore towards inside the collaboration itself, right?
Yeah, I think some people study that, but I have never seen the results.
Yeah. Because it's not straightforward. Of course, this curve, we might expect that it goes up a little bit, right? We don't know how much, but still we are, the values, the range of values of flux, of neutrino flux that are provided by Saqib's solutions are still, in this comfortable in this range. But definitely you are right in this point. And now, with regard to the lower energy photon contribution, yes, actually, we sort of evaluated this through the EBL, because the EBL has also contribution inside the clusters, right? So we found out that this might be enough to account for these low energy photons, right? Using the EBL, because the EBL is there anyways. Towards individual source contributions, actually, it's rather difficult to estimate this directly from these MAGD simulations, from these cosmological simulations, because actually they do not account for the radiative cooling that would then provide more realistic cold structures immersed in the system, and then we could try to compute, let's say, local contributions for these low energy photon fields. But anyways, these low energy photon fields are accounted for through the EBL. But
Yeah,
yes, you right that.
Yeah, but my point is that there are individual galaxies, right? And then the galaxies actually there are member galaxies of the galaxy.
Mm-hmm.
People estimate because the galaxy SCD is also very steady, and
Exactly.
then actually one can compute the photon fields actually provided by the galaxy members, member galaxies as a member of the galaxy clusters, and then this can actually enhance photon fields compared to the EBL. This is actually already, then this enhancement is actually the important to the, for example, if you want to explain the ultra energy cosmic rays, and then in order to explain the OJ data, the spectrum has to be very hard. And then one of the possible solutions to make the spectrum hard is actually disintegration of nuclei, and this enhancement is actually helps the cosmic rays spectrum harder, help the cosmic ray spectrum become harder, and then so in this sense, actually, they take into account this enhancement for the photodistillation due to the individual galaxies can be crucial, especially if you want to, if you're interested in the spectrum of the ultra-high cosmic rays. And also, this also enhances the neutrinos flux around the 10 to the 17 electron range, compared to the just EBR only.
Right. Yes, I think this is a correction that can be implemented to improve these evaluations. Definitely. Thanks for the feedback.
And then I think that regarding the hoax, then maybe you can also check the paper or proceedings by the whole group. Actually, they provided the early preliminary estimates on the upper limits on the diffuse gamma ray background. Actually, this is done by some previous postdoc at Penn State, and then the limits is probably around the 10 to the minus 7 or 10 to the minus 6, which is actually much weaker than what you showed. So that this can be improved, but this actually may actually help you understand the possible constraints coming from the Hawk and Rasa. I think the IC are probably the ICRC proceeding in 2019 or something like that. Then maybe you could check.
2019?
Yeah, I think so. So that I think there are some limits. Actually, it's a preliminary result. Actually, I think that there's a proceeding by the yes. So from the
who's the name? Can you say the name?
At Harding. So Los Alamos.
Okay.
Yeah.
Thank you for the reference.
Okay. Can I ask one more questions, or should I pass to the other committee members?
No, you can. You have 1 hour. Just for you. You may use an entire 1 hour to inquire if you want. Please go ahead.
Okay. So okay. Another question. This is a bit technical question. So when you compute when you implement the actual shear propers, sorry, could you clarify how you compute the diffusion part? So that in principle, you just use the direct simulations. Actually, you actually use a scheme of treating the diffusion part in a separately, because sometimes actually for example, did you check that reproduce, the diffusion coefficient can be reproduced and
So
by using the simulations or not?
So Can you rephrase your question and repeat actually?
Okay, so the way you do simulations and okay, so that for example, if you simply assume the diffusion coefficient and the assuming the simple diffusion, for example, if you assume the Kolmogorov spectrum, right, and then spectrum is actually steeper by some diffusion coefficient index, right? If you say
so we actually didn't use that, so we used the simple ratio of parallel to perpendicular diffusion coefficient, and yeah, we didn't use the Kolmogorov or a spectrum thing. Yes.
Yeah, but the question is that what is actually the effect of you put the injection spectrum, right? And what is the effect of the steepening of the cosmic ray spectrum after the diffusion? Because if you compute the spectrum, the cosmic rays which are confined in clusters, and then this is actually the spectrum is steepened by the diffusion coefficients, right? Even if you don't use the diffusion coefficients, you should see the steepening, right? Spectrum steepening due to the diffusion.
Yes. So okay, so we actually fixed that parameter to a single value, and okay, the steepening actually came at energy 10 to the power 17 electron volt, the spectrum, the cosmic ray spectrum. So if you are asking like, did we explore the diffusion diffusion parameter and really observe that where which one is creating? Okay, so as I show the result for two different values, like if you consider a large parallel diffusion coefficient, then it will then the cosmic ray will will trap more as compared if you consider the large perpendicular coefficient. So this is this is how we implement. And in case of intercluster medium, so as in the literature, or they usually consider that the parallel diffusion coefficient in intercluster medium plasma is larger than the parallel one. So sorry, than the perpendicular one. The parallel diffusion coefficient is larger than the parallel one. So and due to the characteristics of intercluster medium plasma. So this is what we did. So is okay. So we observe that if the diffusion coefficient parallel is if the perpendicular diffusion coefficient is larger, then cosmic ray will escape easily from the structure. So that aspect, like where they are exactly steepening, we didn't studied in detail.
Okay.
Because we are mainly interested in the, you can say, like in the high energy production part and the interaction of cosmic rays and these. In case of steepening, yes, we didn't study it in detail.
Yeah, because this is actually kind of interesting, because this kind of question can be in principle interesting if you want to make the more quantitative comparison with neutrinos data, and if you want to compute the cosmic ray spectrum in the more quantitatively, so to actually to fit the data, this actually can be important questions. Actually, this actually affects the fitting result.
Yes, because okay, so our results are already very, like you can say, sensitive to cutoff energy or the spectral index we choose.
Yeah.
So, okay, if we like play with the diffusion parameters or the diffusion, then okay, we can like match with the data. Like we can optimize the parameter better and then match with the data better. Yeah.
Okay. Good. So the other technical question: what is the lowest energies of the? How much? What is the minimum energy cutoff for the cosmic rays you inject in the simulations? So what is the minimum energy? Just a technical question.
Okay. In case of, so we tried. Okay. The minimum energy for neutrinos, we are injecting like from a range 10 to the power 14 to 10 to the power 19.
Oh, for the cosmic ray energy.
Yes.
10 to 14. Okay.
So this is the injected part. Okay, and it is okay for we are as we show the result for different cutoff energy for 10 to the power 16 and up to 5 into 10 to the power 17. We show the results. So Yeah, so this is
basically the how about the fate of the cosmic rays with the 10 to the 14 electron volts? Did you see that these 10 to the 14 electron volts cosmic rays are confined for basically the cosmic time, cosmological time? So basically almost.
Okay, so yeah, we can say okay, the low energy cosmic ray like 10 to the power 14 and 15. So they completely confine. Okay, and but it's like it depends on the magnetic field basically in the cluster mass as well. So if the cluster mass is heavy like 10 to the power 15, so it will completely confine like larger than, you can say, like Hubble time or something. But okay, so I will again say it's like we didn't estimate it like in detail, like if we inject that cosmic rays, it will confine within that structure for how long. And I didn't, we haven't studied like in detail that. So okay, but what we studied, okay, so if a cosmic ray, if a cluster mass is that much and the magnetic field is this much, then you inject this range and then what you get. So actually the steepening, or you can say the high energy cosmic ray, of course, above 10 to the power 17, they escape easily, and the other one confined. But again, I say it will depend on the cluster mass and magnetic field and density as well.
Okay, but you qualitatively check that when you are running simulations.
Yes.
Okay, that's good. Okay, one more question. This would be the kind of final question from me. So when you actually compute the effect of the evolution, the basically star formation rates, the agent evolutions, I'm a bit confused about normalization. Then I think that when in the plots, actually your crux is actually the star formation rate case is actually higher than the AGN case. But I think that the evolution itself is actually stronger for the AGN, in my understanding, based on your simulations, what you use. Because I think that in your calculations for the AGN evolution, the low energy index, the evolution index around 5 or something like that, in my understanding, right? You're right.
Okay, in case of AGN, okay, the AGN evolution.
Yeah, the reason why that you get the rate is actually the flux is higher for star formation rate is actually due to the normalization, I guess. Then why you take the different normalizations? Do you have any specific reasons for this choice of normalization? Because if I use the same normalization at the redshift 0, then I expect that the AGN evolution is actually can be higher.
But AGN evolution, what I saw, it's like, okay, it's more dominant in the high redshift part, like, and star formation, okay, it's okay, it's less dominant, you're right, but it's like give you in the lower redshift interval like less than 1. So they are so less than 1, so they are kind of competing with AGN, but still low. And as the major contribution come from the very low redshift interval, like up to 0.3. So in case of their contribution, because if their functions are normalized, so the effect due to those both functions is going to be the same. Yeah, almost the same.
No. If you actually assume that if you normalize that the redshift 0, then of course if the evolution is stronger, then basically the flux is higher for the stronger evolution, right?
Yes, you're right.
Then this means that if you actually use a normalization, if you use the same normalization factor at redshift 0 for both AGN and star formation rate histories, I think that AGN evolution is actually that gives a higher flux than the star formation rate flux. But the reason why you get the higher flux of star formation rate history is that probably that you assume that the larger normalization factor for the star formation rate history. Then the question is that do you have any reason why that you take the higher normalization for the
so because so the AGN and star formation, so the evolution is defined by different functions.
Yeah.
So it's a different redshift dependence. So then the normalization factor will be different for both, isn't it?
But how do you determine the normalization factor? Because if you, in principle, I can take just normalization, just redshift 0, right? And in this case, evolution is equally redshift 0. You can normalize that, the normalization factor, the redshift 0. In this case, a stronger evolution gives a higher flux. But then you can start to change the normalization factor for the two evolutions. Okay, what is a proxy? How do you determine the different normalization factors? What is the reason? Just as I'm asking. So yeah, so
it's like
Saqib, go back to the equation and try to answer more quantitatively.
Now the voice is lower. Do you want to use a headphone?
I think they're listening
Oh,
clearly.
yeah, okay. So here, so A and B. So basically, if I use just because redshift 0, if I put so the A equal 1, B equal 1, then the actually is yes. So in this case, agent should win, right? Yeah. But the question. Yeah, but my guess that you probably adopt a different normalization. Then the question is that probably you basically B over A is not 1. Then how do you determine B over A in your computation?
So it's okay. So you integrate the function and then you normalize with that number.
Yeah. Because typically normalization, the redshift evolution is actually just, for example, you can introduce evolution factors in with a normalization such that this factor is 1 at redshift 0. And in this case, okay, so the stronger evolution gives a higher flux, right?
Okay, so in this case, so I integrate and up to maximum redshift and then divide with this number in both cases. So, but as the functions are different, so the number gonna be different, isn't it?
Yeah, but if A equal B equal 1, then I think that in the both evolution factor, both function is normalization is 1 at redshift 0, right?
Mm-hmm. Yeah.
In this case, stronger evolution. In this case, AGN actually gives a higher flux. You agree?
Yes.
Yes, and then but I think that your case actually, your flux is actually opposite, right? So the star Hermitian right history gives a higher flux. This is because you actually choose the different values between the B and A. My question is that what's the reasoning of the different values of B and A?
So the reasoning, okay, it's simple as I told, how I did it. So that's why, because they are different function and I got different A and B. So, and okay, yeah, I didn't normalize it as you're saying A plus B equal to should be equal, yeah.
Yeah, because I think that B and A is actually to me that this normalization looks ad hoc, and then I think that so for the apple to apple comparison, though, just apple to apple comparison, which reflects the only effect of the evolution, then it's better. I think that usually we usually consider the same normalization. Basically, the redshift of 0 is 1, right? And then you can make apple to apple comparisons among the no-redshift evolution, star Hermitian right history, and Asian evolution. So if you start to adopt different normalizations then probably I think it'd be useful to give some reasoning, right? Otherwise, actually, I'm a bit confused about this ordering because this ordering is actually flipped because of different normalization.
Can I make a point here?
Yeah.
But they are actually there is no reason why the normalization should be the same, because they are different population.
Yeah,
right.
But this is a different population. This means that you have physical reasoning, right? If you just ask the evolution effect only, then okay, the people usually say that redshift evolution star formation like history, agent like histories. And in this case, this actually just reflects evolution, effect of evolution. Once you adopt the different evolutions, maybe that you adopt some physical assumption, right? So then maybe that you assume that okay, only fraction of the clusters may have AGN, and basically this affects this affects actually this affects the normalization factor in that ratio zero. Then maybe you can say that the AGN fraction of AGN, basically AGN is rarer than the usual galaxy, right? So the most of the member galaxies are just usual galaxies. The AGN is actually the rarer than the usual galaxies. You have some physical reasoning, right? And then that actually this is actually different. This is actually the effect is different from your evolution effect.
Excuse me, there's a lot of background noise here from a tractor, some kind of vehicle. I'm going to change it for headphones. Excuse me. Aqui, mouse.
Oh, okay. So you mean that
we can't hear you well. Just a minute.
It's not a problem at your end. It's a problem at our end.
The problem is
okay.
So just wait. Yeah. Little.
Okay. Now it's better.
Acho que é esse aqui. Ouviu? Turn on.
So you can speak now. Yeah.
Oh, okay. Yeah, just I asked that this question just because this is a different normalization is okay, but you need to give some physical reasoning, right? This is a different from the effect of the evolution only, right? Just I asked the evolution effect. Basically, of course, stronger evolution gives a higher flux in this sense. Then it's okay to adopt the different normalization for the different. Then you can flip the order, but the question is that what is the meaning of this ratio, normalization ratio? Then that my question is that I wanted to ask you how you decide this ratio itself.
Yes, I think this should what Kohta means is that this should be further justified in the thesis, right? Why the adoption, since we have these two classes of populations with different evolution history across the redshifts, but anyways, why the adoption of a different based on this, but with the physical meaning behind this, right?
Yeah. Because otherwise I kind of get confused because the pure is just to use the same normalizations, and actually the AG evolution in this definition, the AG evolution should give a higher flux because evolution is stronger. Then you have to assume that you need to. It's kind of it's better for you to give some physical reason than for the different normalization.
Right, because in principle, what one tries to match is, okay, if you have a different evolution history, then at a given redshift, you might use some kind of observation to constrain these values, right? A and let's say the constants, right? So your point is that, okay, if you try to fit this for z equal to 0, why is that you get this difference between them at this point, right? Okay, so yes, I think the difference is really small, but this might be justified accordingly.
Because this actually qualitatively flips, right?
Exactly. All the rest. Yes, that's true. You can adopt. You can assume that at least barely know the values of these constants at a given redshift, and then you normalize accordingly.
Okay, so basically these are kind of questions. For the thesis part, I think that I let them. Yes, I think it's well written, but I still think that maybe it might be useful to just for the comparisons. Actually, it might be good to check for example, you say that effectively okay, so in understanding most of the contributions come from the low redshift clusters. That is true, especially if you don't incorporate the Asian or basically but if you start to consider Asian or evolution or Asian star formations, basically effective evolution is determined by the convolution of the galaxy clusters and the astrophysical objects which are contained in the galaxy clusters. And I'm still kind of curious about if you use mass functions based on the observations of the galaxy clusters or n-body simulation, what is the impact of basically what is the difference between your simulated mass function and the mass functions using the literature. And you probably already said that it's probably consistent, but just based on the results of your gamma ray background, I still wonder that there's some difference, and which could be which could be important as a possible explanation. Then maybe it might be kind of useful to clarify the difference and the physical reasoning of the why the accelerated gamma ray background you obtained is flatter than the curve obtained in the previous literature. Okay, this is just my suggestion. Okay, thank you very much for the answering my questions, and that's so far these are questions I have.
Okay, thank you.
Thanks a lot, Kohta, for your questions and your comments. They are very useful and very welcome, and will be investigated, further investigated. And in fact, I doubt that the results coming from anybody simulations would be better than those, because, as I said, these are more complete, because they combine these cosmological simulations combine anybody interactions with the gas interaction. So it's more complete in this sense. But of course, we must compare, provide further comparisons, and also with the observations. We should note that in the case of neutrinos, for instance, Fang and Murase and Olinto, they employed semi-analytical functions based on observations and n-body simulations. And we found that the total neutrino flux is of the same order, but the contributions come from different mass distributions, right? And the different redshift. So I think this is a key point. And we wonder, or we inquire, that the cosmological simulations provide a more fundamental, a more detailed answer to this. So this is our arguing on this. But definitely this can be further explored. This was only the first attempt in this direction, right? But definitely we can improve the cosmological simulations, and also the corrections, the functions, the cooling, the radiative cooling, that the feedback of the forces of individual forces that remove part of the mass of the clusters. So we corrected this, with this F function, but we can improve this as well. And with regard to cosmic ray diffusion, your comments were quite appropriate, because we left this diffusion coefficient as a free parameter, because we had so many issues to explore in this work. But yes, this actually is a fundamental question, and deserves, actually by itself, is another PhD work, right? And actually we have a student exploring cosmic ray diffusion for lower energy cosmic rays, because this is even more important for lower energy cosmic rays. But but it is something that, as you said, is very important and fundamental to explore, and we are doing this as well. I mean, in another separated work that deserves another PhD thesis. But a lot for your input. Your comments and questions are really very, very welcome, and we are going to explore these issues further, all your suggestions and inquiries. So can we move on now? Shall we go to Rafael, because Rafael is in Spain? So actually you are even further away than thought, but my mistake, my geographical mistake.
Yeah. Okay, so thank you very much for this presentation, Saqib. So I just jumped in last minute. I have a couple of comments about the talk and a couple of comments about the text itself. So one point that I'd like to discuss with you is essentially something more broad to start with, is if we go to, your plots are not numbered, so it's hard to refer to them, but in one of your plots, you have shown the red band for the diffuse gamma ray background coming from your simulations. It's the band with all the parameters, with all the spectrum indices and all the maximal energies and so on. Yes, this one. So part of this parameter space, it's already excluded by Fermi-Lat measurements. I know that, of course, the intention here is just to show the parameter space covered. It's not to make any exclusions, but have you given it some thought on what part of the parameter space of neutrinos you would be able to constrain by taking the region of this parameter space in the red-pink curve here that would correspond to neutrinos? Because there is a combination of spectrum index, maximal energy that you've used that will overshoot the diffuse gamma ray background. This combination of spectrum indexes and maximal energies will also constrain the maximum neutrino flux that you'd get. Have you given it some thought on what would happen if you try to combine both results? Are you speaking? I cannot hear you.
Saqib, your microphone is off. Turn on your micro.
So now you can hear me.
Yes, yes.
Okay, so yeah, first of all, the parametric range we are using here, it's almost the same as we use in the neutrino. Okay, so especially for spectral index is, okay, from 1.5 to until 2, so it's basically overshooting. Because in case of neutrinos, as I show the result for different parameters, actually, I think it's better if we just go. Yeah, here you can see like so 1.5, 1.9, they are overshooting basically. So it is the same like harder spectral index, like above 2. In case of gamma rays as well, that's also overshooting. So that range automatically excluded. So with respect to both sides, like gamma ray results and neutrino part as well. In case of maximum, the cutoff energy. So in case of cutoff energy, up to 10 to the power 17, it's okay. In this case, as you can see, like for spectral index 2, okay, in spectral index 2, the results are not matching. Okay, they're a bit below, but they are overshooting if the spectral index you like it's above 2, like 1.9 or something. So I would say, okay, the parametric range which is excluded, or you can say which make the better combination to fit or to match with the ice cube or the Fermi-Lat is above 2, and the cutoff energy is 10 to the power 16, and between 10 to the power 16 to 10 to the power 17 electron volts. So that would be a best parametric range to match the data.
Okay, so what you're saying is that the overshoot would come from the increase in Emax.
Yeah, increase Emax, and if the spectral index like 1.9 and 1.8 or these, if it's below 2, then yeah.
Okay. Then I would be actually.
Just let me. Okay, here you can see for spectral index 2, even for spectral index 2, okay, our results is like overshooting, but okay, we don't have any Fermi-Lars data points. This thick black line, okay. Here, or you can see like here in both curves, like the thick black line. So the spectral index 2, okay, our flux is much higher than the Fermi-Lars data points, but it's if there are data points or whatever, or in a sense you can say it's even overshooting the Fermi-Lars as well. A spectral index 2, but not in case of neutrino flux. So in this combination, I don't know if you. So yeah, this is.
Then in this case, I have 2 points just to continue on this. The first one would be, it would also be nice to see the same plot with this band for neutrinos. It would be very instructive, actually, and especially if you put them side by side, because then you would be able to discuss both of them together. You started your talk in one of your first slides. You were saying, okay, we are trying to explain cosmic rays, neutrinos, and gamma rays within a single framework, everything together at the same time. But if you want to do that, you have to say that, the point. You have to say that if the lower limit of this plot that you are showing already overshoots the ice-cube measurements, then something is wrong, right? Because you are saying that clusters can contribute to the gamma ray and the diffuse flux. You calculated both, but you have not shown that they are compatible.
Okay, yeah, I understand.
Yes, so that would be a suggestion in this direction, to have exactly the same plot for neutrinos. And the second point is regarding the Fermi-Lars data points. As you know, these data points from Fermi-Lars, it's from, I think, 2014, if I'm not mistaken.
15,
15, yes. So the way it's computed, it's by removing the galactic foreground.
Yeah.
In that paper, there are at least 3 models of galactic foreground that would lead to very different data points, especially at the highest energies.
Yeah, you're right.
So your conclusions, if to be able to say that there is some kind of overshoot or not, it depends on which foreground model you are adopting. And just by looking at it, I haven't seen this before, I'm just realizing this right now, is that the last point of Fermi-Lars, it's ending at 7 times 10 to the 11.
It's round, according to the paper, it's like 820 if you see the right error bar, right error bar, 820.
But then this last point, it should be an upper limit. It shouldn't be a measurement.
Okay, yeah.
Because
I think it's not upper limit. Upper limit is I don't know, in the you can say another paper they show that point, actually the upper limit thing.
Okay, so this last one, it's a measurement, it's not an upper limit.
Yeah, it's not.
Okay, correct. So the point here then that I would like to make is just that your results, your interpretation depends a lot on the foreground model adopted. Okay, now moving on. Everything that you did here was for cosmic rays in the energy range between 10 to the 14 and 10 to the 19 electron volts.
Exactly. Okay, 11 to above.
Yeah. I understand the reason why you did that, but you assumed a proton composition, and as Kohta already said earlier, for example, things start to change if we assume a heavier composition, right?
Yeah.
Did you study any cases of a heavier composition, something like helium, nitrogen, or iron nuclei?
Okay, I studied, first of all, I produced some preliminary results for individual clusters and see if if there will be a more a production of gamma rays or neutrinos for heavier nuclei. So I find it's not, and I see in the literature like for example Kohta et al. They also computed the contribution if they consider the heavy composition of cosmic rays. So because the photo disintegration decay will be more important for heavier nuclei, and then the result will, okay, it may affect the result if you consider a mixed composition, but okay, I haven't estimated yet, so my comment, it may not affect a lot, like the you can say the total flux may not change that much. Okay, it will affect the shape or something, but with the total flux will not change that much, because especially due to photo disintegration as well.
Okay, but what you are saying is that the total flux of neutrinos would not change due to photo disintegration if you assume that you are talking about cosmogenic neutrinos. But if you start including the gas in the cluster and the photons in the cluster, things change, because the interaction, it's not straightforward.
Yeah.
Right? There are new interactions, so you can not simply apply the reasoning of CMB and EBL as you are used to talk about the neutrinos in the cluster for a different composition. This is true only for cosmogenic neutrinos.
Yeah. You're right. So that's I did some preliminary study, so I don't have any like complete conclusion about that. But yeah.
Do you have backup slides on that?
Saqib, those plots are in your thesis at least, but no, I don't remember if you put them in the backup slide.
I have. So.
Okay, yeah.
But I don't know those results. Okay, this was the. Okay,
yes, you do have.
No, this is the. This is not. This is just to show the mean free path, and as you can see, the photo disintegration is much more important for heavier nuclei by the dashed line. And about the preliminary results, okay, yeah, there are some, but okay, so these are very preliminary, and even the units are in the like these are simulation or code units. So I estimated these kind of fluxes like for proton, for nitrogen, and for iron, and so these are the neutrinos. So the statistics is not enough, so you cannot say like anything with the perfect certainty. So yeah, this is I have. So okay, like I have even plan, and it's like based on my studies or the tools we have. It's very like it will be very straightforward to study with the different composition and how the result will change. Yeah.
Yeah, but going back to the previous slide in which you showed the mean free path, or actually 3 slides. Yeah, this one. Yeah. You again are apparently, at least in your explanation, you were not making it clear. Although in the thesis it seems to be written correctly, but you are not making a clear distinction, at least to me, in what you are telling me, because your answer is still about the propagation of proton, helium, nitrogen, and iron over a given distance, assuming cosmological photon backgrounds. Yeah. But your whole work is contained within a cluster of galaxies.
Yes.
Right? So these are different. There are additional photon backgrounds there.
Yeah.
So what can you tell me about these additional photon backgrounds? Because they might even dominate over the cosmological ones.
Okay, so as we checked the first one, the Bremsstrahlung photon field, and that seems to be not important, at least for the photopion production. But the cascading process, it is important, inverse Compton and other cascading processes. So and the photon field which Kohta actually suggested, so they may also interact with that also will make difference if you consider the heavy nuclei and even with the proton, because we didn't consider those interaction. So yeah, Bremsstrahlung photon field, and also the cosmic ray interaction with the gas as well. So because then proton-proton interaction will that will further decay to smaller mass nuclei, and so I would say like it's quite complicated to say anything, but yeah, so because okay, so if there is a heavy nuclei, it will further disintegrate to smaller nuclei, and okay, ultimately the proton population or the density will increase, but during the disintegration, it will also produce neutrinos or gamma rays as well. So, and this will change the result entirely.
Yeah, just I can give a comment. So basically yeah, I think as I told you, the additional photon fields actually from galaxy members are important, and actually this affects the photon integration. But neutrino flux actually found to be basically consistent with the proton case within the large model uncertainties. Of course, hadronic interaction parts, basically the PB neutrino flux, which is relevant for IceCube range, it does not change much, right? And then this affects actually the flux of the 10 to the 17 to electron, 10 to the 18 electron volt range. Yes, but still, as long as you assume the steep spectrum, still the protons, the photopion production from protons actually is still important. So in that sense, actually, results are not super affected by the composition, but probably if you start to play games, the spectrum index story is different, as you can imagine, right? Then if you start to play games, the spectrum index and the harder, okay, then in this case, photodisintegration is actually more important effectively. And then basically, as I told you, the additional photon fields break up the photodist nuclei, and these kind of secondary nuclei is actually the affects the resulting spectrum, the neutrinos. I think that in this case, you should be more. You should be able to see the more difference between the proton and the heavier composition. Just comment.
Okay, just picking up on your comment, then, Kohta. But there are two factors here. This is an interplay between what happens in the interactions themselves and the magnetic field. If we have a heavier composition, let's suppose iron. Iron is 26 times proton in terms of magnetic confinement. Yes. Therefore, you can have, even if the given infrared path for an iron nucleus is 26 times smaller than that for proton, the magnetic confinement will make them comparable. Therefore, I'm not really convinced that this analysis is as simple as that, because this has to be simulated at some point.
Yeah, I think we simulated, right? So indeed, the confinement helps the spectrum harder for the nuclei. That's actually the two effects actually to make the, for example, this is a very important to explain the spectrum of the data, right? Because the confinement of the heavier nuclei and the disintegration of the heavier nuclei due to the additional photon fields makes the spectrum harder, which eventually fits the help you to fit the data better. So in this sense, your points actually I absolutely agree with you. These are non-trivial, but indeed they are important if you want to make a detailed comparison.
That's true, in fact, and this also justifies why it's so important to account for an appropriate, more realistic background with using MADD simulations, cosmological, rather than anybody's simulations, for instance, right? That do not account appropriately for the background gas and magnetic field distributions. But yeah, definitely this discussion is very important. And all these effects have to be accounted for in the future, of course.
Yeah, Saqib, I have another question. Then, in your definition of a cluster, you just put a sphere around the center of a cluster, right?
Okay.
Yeah. How good is that definition? In the sense, how much could it affect the results?
No, okay. First of all, I didn't put, I put a sphere at the edge to observe, or you can say outside the cluster, or to contain a cluster. And okay, so that definition, it's not like, because we explore the whole imagery simulation up to redshift 5. So it's almost like we didn't find any cluster which is completely spherically symmetric. So like you can choose the radial profile, or like the distribution of temperature or magnetic field is, it can be considered like a spherically symmetric, because I showed some of them, like the distribution of magnetic field. I can even go to that slide. So, and because you can clearly see that distribution are not spherically symmetric. So, and if it's not spherically symmetric, so then it will affect the emission pattern. So it will be different in different directions. So depending on the, so, and that's why we use MIG simulation and implement or use the magnetic field distribution as it is we obtain from the MHD background. So the spherically the schematic diagram I showed, of course I showed there's a sphere and we are collecting at the edge of the cluster, but the distribution of magnetic field and the density and the Bremsstrahlung photon field, that's the main thing which you will consider the interaction with. So we consider they are not like as spherically symmetric at all. We consider it as it is from the 3D MHD simulation. So as far as your question concerned, that how good is the definition? Okay, in case of that symmetry, so it doesn't exist, seems like that.
Okay, since you mentioned the symmetry, that your clusters are not spherically symmetric, one individual cluster is not spherically symmetric, but the average cluster population might be, right? Therefore, your results might not depend on the asymmetries inside the cluster. Or what do you think? Could you elaborate on that a little bit more?
So my result may not depend on the distribution, you're saying?
Yes, because one cluster, you can see here in the plot, yeah, it's not exactly spherically symmetric, but the whole population of clusters, on average, might be, right?
Oh, okay. In case of on average, I would say still not on average because okay, so different cluster have a different shape. Okay, on average, so when you are calculating like the total flux from the entire population, okay, so then it's not gonna make that much difference because okay, you're already averaging out the total focus. So you choose some clusters in at one redshift and some cluster at other redshift, and then simulate the neutrinos and see the effects, and then average out the total flux. But okay, so if you study like the individual cluster in like detail, suppose like we are just considering like very high energy gamma ray emission, in that case you can say the symmetry is not I would say not that important, but if you probe a single cluster and study the halos or like low energy emissions, so then you cannot ignore that. So okay, on for the total flux, okay, you have to you are in a sense right, and like for the entire population you average out. Okay, so you may say like they are on the average have some symmetry, or you can consider radial profiles. So and yeah, but I would say that would be a more like say crude analysis, or you can say the guess as compared if you done that simulation and then you can see like more realistic view of the cluster, and then your result will be more accurate, let's say, or like more reliable or certain. That's like what we actually did. So we explore the whole population with different mass range at different redshift to see like if it make what difference it that deviation or the actual distribution will make.
Okay, thanks. I have now a couple of questions about the text of your thesis.
Rafael, may I just complement Saqib's comment? Yes, sure. Saqib, and then actually you have tested and compared with the Fang and Olinto, for instance, for the neutrino distribution, and you find out that although the flux is more or less the same, the contribution from different cluster mass populations and different redshifts is striking, right? So symmetry may be one of the issues that have provided this difference between our results, your results, and those of Fang and Nolinto, right? So just a quick complementary observation to your comment, Saqib.
Yeah, and in case of gamma rays, okay, we have one issue to discuss or fix in case of gamma rays, but still our results are different from almost all of them, actually higher. So that also may be the case, like that symmetry thing, yeah.
Yeah, makes sense. So I have a couple of questions about your thesis. I don't want to go into the details about that, but just some conceptual things that I've noted. The first one is in one of your equations. I don't know if you have your thesis there, the text.
I don't actually. It's in this system. So.
Or the PDF in your computer.
In my computer, but I'm presenting from the.
Okay. So in any case, my point is that this is not an explicit thing. I won't go into much into details, but I just like to identify whether this is something, maybe just a typo or if it's a conceptual issue underlying the thesis. Because in the text here, when you write the mean free path for a given interaction, you write it in terms of two integrals, right?
In terms of what?
Two integrals.
Two integrals. Yeah.
So can you tell me, when you compute the mean free path for a given interaction process, what goes in it?
Which, I don't see the equation. So it's like cosmic ray energy, and then you calculate corresponding to that.
Yeah, but the details, the kinematic part. So what does your mean free path is telling you which quantities go in it, like the cross section and so on. Yeah, because in one of your equations, the point I'd like to make here is that not in one, in all the equations that you wrote in your thesis, you calculated the mean free path according to the right quantities as expected, and the right quantities are usually when you're treating particle interactions, you have the center of mass energy, and the center of mass energy, in our case, let's suppose you have a cosmic ray, and then you have a photon, and it's the center of mass energy of this process. You also have, if you're doing this treatment in the laboratory frame, you have the energy of the proton in the laboratory frame, right? And you have the energy of this photon in a given frame, also the laboratory frame in this example. But everywhere in your thesis, you wrote this as two integrals. And this is kinematically incorrect.
Okay, so maybe I follow up, you can say, a style from...
So yeah, I just like you to explain to me. Yeah, it's hard since you don't have your thesis with you, not even the PDF. But yeah, I would just like to understand if it's just something that you wrote wrong and you did not use it wrong in the calculations and so on. What goes into the calculation of the mean free path? That's my question, essentially. All the details, the mathematical details of the equation.
Can I tell without seeing it? So.
Yeah. Okay, then if you don't have it, just leave it. The point I'd like to make is that all the equations in the thesis are wrong because you split the integral in two parts, and this is a double integral. It's not two separate integrals. Why? Because all these processes, they have kinematic thresholds, right? For example, if you have pair production, you
said it's a double integral, and what is not? Can you repeat that?
Yes, all the integrals in the text of your thesis of the mean free path, all the calculations, they are showing two integrals. The first integral is one. Let me open it here. Yeah, it's here. It's one in the center of mass energy, so S, right? You integrate first on S, and then you have a second integral over epsilon, in which epsilon is the energy of the background photon. But this is not correct. Because if you have some process, let's suppose you have pair production, like photon-photon producing electron-positron. This process can only happen if the center of mass energy of both of the photons is higher than the energy equivalent of two rest masses of an electron. So an electron plus a positron, right? So that gives you a given energy.
Yes.
And then the two photons, they have to have combined the same energy. So if you don't have if you have two separate integrals instead of a double integral, you are not accounting for this dependence on your equations.
Oh,
so,
okay. Okay, it's a double integral. I calculated everything in the double. It's not like they are, and they are not separate like and like I'm integrating separately and multiplying. No, it's a double integral.
Yeah, but they are written separately. It's like you have two integrals. The point is that the limits of integration of one depends on the other. I think
maybe
this should
so.
be
I think you are saying I write like one integral and sum of the quantity, and then second integral some quantity. Yes.
Yes, you are writing f of x dx, the integral of f x dx times the integral of
it's not
g of y dy.
Yeah,
which is wrong.
Yeah, okay. I should put the two integral first and then the whole quantity.
Yes, because the limits of integration, they depend on each other.
Yes, it's connected and you cannot do. Yeah, you're right. Actually, I understand what you're saying. Yeah.
Because that's essentially the physics of this process, right?
Yeah.
You have the kinematics.
Yeah, otherwise even like, I don't know, you cannot even calculate because if you don't connect them, the integration limit.
True.
Yeah, so it's like automatically, okay, yeah, I will fix that notation. I think it would be like better to remove the confusion.
Yeah. And also in your thesis, again, there is something here that it's confusing me. Since you don't have it, I'm just going to ask. Can you still hear me?
Yeah, I can. Yeah.
Okay, because the image froze. Can you tell me, I'm just asking this because in your thesis in the text, I find this a bit inconsistent, but can you tell me a little bit more about what the Bethe-Heitler per production is?
It's when it's a hadronic process. A proton will interact with the photon and produce pair production. Okay,
then you said the hadronic process, right?
Yeah.
Okay, because in the thesis, you started writing the Bright-Wheeler pair production, which is photon-photon going to electron-positron in the first paragraph, and then in the other paragraphs, you mix this up with the Bethe-Heitler pair production, which is hadronic.
Oh, okay.
So this is section, I can tell you.
Yeah, that's I know. You don't even need to tell me. I know which section is it.
Yeah, this is a typo, in fact, that I remember that I quoted, and probably Saqib forgot to.
Yeah, maybe I couldn't, because he
forgot to. Yeah. Yes, he forgot to correct. And yes, about the integrals. Yes, definitely he calculated correctly, but yes, there is a typo. I checked them. I checked them right. Yeah, this I missed this as well in the equations. Yeah, thanks, Rafael, for calling the attention to this one.
Yeah, so I have just one last point, which is something very more general. Can you just broadly comment on the implications of your results since you calculated the diffuse gamma ray flux from clusters of galaxies and the diffuse neutrino flux from clusters of galaxies? Could you just better frame the implications of your results more broadly?
Okay, so as I kind of said, so the first broad, or you can say the ultimate broad application of the results. Okay, so we use the most detailed method to calculate these high energy fluxes from a cluster of galaxies, considering the whole population from up to redshift 5 and the mass range, from the possible mass range, which is considered to be a cluster from 10 to the power 12 to 10 to the power 15.5. And so we conclude, or our results are matching with the observation, with the diffuse fluxes of neutrinos and gamma rays as well. So in case of neutrinos, there are some other studies as well, and they are also matching with them as well. So they are, like, you can say with some certainty that these results or the neutrino flux might be observed in the future by the next generation ice cube or might be at least constrained better with respect to the cluster population. Until now, nothing haven't confirmed or observed from the cluster population especially. And okay, in case of gamma rays, so okay, I will say again, that's the most detailed studied or the simulation work we did to estimate that flux. So in that case, so it's like, and our results are somehow like give the impression that they are like overestimated from the whole population, as they are like surpassing the Fermi law data as well. But even like, so that's the most detailed calculation we did. And so, and we are expecting that maybe next generation telescopes might confirm or like disconfirm it. And yes, we there's the more like broader picture, or that picture or that those results is a step forward in a sense that, especially in case of diffuse gamma ray background, because the individual sources are mainly contributing in the low energy, or in case of diffuse, up to 10 to the power 11, 5 into 10 to the power 11 and below. And so there may be observation, or there are like diffuse gamma rays above that energy. So I would say the clusters may be, as our studies is telling, that the cluster might be able to produce them, and as our results at least saying that. So, and to diffuse to so our the cluster contribution to diffuse gamma ray background can be very pronounced. So until now there is no like surety like where this flux come from, or like, okay, so there are studies which are saying like this source may contribute the most and this source may contribute the most. Especially for gamma rays, we are saying the cluster can also contribute to a very large fraction in case of gamma rays. So like this is the of course there are many issues, or like you can say many other directions to work to improve those results. But in a sense, it's open a new window from a cluster of galaxies that they can also produce diffuse gamma ray flux up to at least some fraction. So that's the, you can say, like the broader picture of my results. Okay, the future, you can say, the work I can do in this direction, that's, I'm not commenting here, but yes.
Okay.
And also, Saqib, you should complement that these results are fundamental, very important to population studies, the contribution of individual population studies, and also to dark matter studies, right? Because if we are providing clusters, integrated contribution from clusters to the highest energies in gamma rays is that important. It means that some future claims that dark matter, any contribution from dark matter at those energies should be confronted with the astrophysical contribution from clusters themselves, if these results are correct, right? So if these results are that robust, so it has important implications for these dark matter studies as well.
Yeah, because right? Cluster of galaxies are the most important sources to measure the dark, or at least to probe the dark matter sources. So yeah, so they have an important contribution in that direction as well. Yeah.
Okay, I think this is enough from my side.
Thank you.
Thanks a lot, Rafael, for your input. Yeah, in fact, all these comments are very important from both of you so far. And so let's go to the next. Ulisses, are you around still?
Hello. Hi.
Okay.
So yes, I'm around and I'm awake. It's been a very interesting discussion, so I'm following it. So yes, thanks, Saqib. And well, a lot has been said already, and there was a lot of discussion stimulated by the questions from Kohta and Rafael. So let's see what I can add, and perhaps I look more from the experimental side. So I have planned some questions here, and perhaps I would like to go back to that point that was raised by Kohta, and then also Rafael touched upon. If you can go back to the previous plot where you have the the red band, the large red band.
Okay.
Yeah, so I agree with the comment of Kohta. I'm almost 100% sure I didn't, of course, check the curves, the numbers in detail, but I believe these are curves for the differential point source sensitivity, and therefore I think it's not very productive in the sense of the understanding. I guess it's counterproductive to show these curves here because they are only valid for point sources. So you cannot really infer from these curves the expectations for observations from the various experiments. And as Kohta mentioned, for the pointing instruments like CTA, for example, this measurement of the diffuse, all-sky diffuse gamma ray background is very complicated. And I haven't seen, as you know, I'm also a member of CTA, there are no firm expectations for the observation of that from the side of CTA. So that's a very, very complex measurement for a pointing instrument. And even if you consider, I mean, the large field of view, that's okay for extended sources with a dimension that is less than the field of view, or can be more when you consider the divergent pointing, and that we can do something about that. But for the all-sky diffuse emission, it's really complicated. And even for the all-sky instruments like Hawk, that's also complicated. And I would have to look at the literature to see if there are some comments about that, or some curves, some expectations from Hawk. But certainly, I guess it's not the one that is shown there. Now, for LASSO, the thing could be a little bit different, because essentially LASSO operates in a background free regime above 100 TeV. So above 10 to the 14, LASSO is able to suppress cosmic ray background with a factor of 10 to the minus 5, which means that from 10,000 cosmic rays, there is only one that is remaining as background. So this is very, very strong. So this very powerful gamma hadron separation for the kilometer square array of LASSO, which is this deep curve that you see here around the 10 to the 14 in the sensitivity, that region, LASSO operates background free. So in principle, it is simply counting photons at this very high energy from whichever direction. And you could contemplate some limits on the diffuse emission. But it's still the number of photons coming from there, the statistics is low, and one has also to be cautious to say something certain about a possible measurement. I mean, this measurement of the diffuse background is something that Jim Cronin, for example, was attempting or contemplating, for example, since Casamia, which is 30 years ago, I guess. So, but it's a complicated measurement, so I don't think these curves, if I were you, I wouldn't show. I mean, it doesn't really help in understanding what's going on, and it can confuse the expectations. And even for LASSO, in this background free regime, but then it's at the very edge of your curve, of your band, because it's above 10 to the 14. So I'm not sure that's useful. I mean, this would apply to individual sources. So what then you could do is, and that could be interesting, you could look, for example, at the fact that, for example, Hawk, and LASSO after 1 year integration haven't yet reported any detection of individual sources, and see how this could limit your expectations in the diffuse background if they force you to reformulate the expectations of the flux of individual sources. But that's completely the other way around. So it's the inversion of the logic. So you use the fact that Hawk and LASSO have not seen anything, and you see if this puts any interesting limits to you in your expectations of the diffuse emission. Consider your source and evolutions and everything else. Yes, the cosmological distribution of sources, etc., etc. So you start from a constraining the modeling of the one source, of the single source that was not observed by Hawk in 5 years or by LASSO in 1 year. So is this comment clear?
Yes. Yes, I understand your point. Yeah, and to include maybe the LASSO background, but yeah, it's also even complicated. Yeah.
Yes, I don't think these curves are useful there. I would take them out because you are comparing two different things: point source sensitivity with diffuse emission.
Okay.
So let me see here. I have a few questions more. So one thing that was in figure 5.6. So now let me look at this 5.6 to remember which one exactly is this from your plot. So I don't know. So this is the one where you show the flux comparing with the works of Nishiwaki and Zandanel.
Yeah, I think
Yes.
I think this one. Yeah.
Yes. Yes. So I think Kohta already touched a bit on this, and in your work there is a very large excess in the highest energies, right? So compared to the other models. So can you explain me a bit better? So where does this come from? This
my results, or you can say the flux come from?
Yes, the excess. I mean, your curve goes has a very high excess compared with the orange line and the blue line. Yes, in the high energy flux here above tens of TeV.
Okay, so as I explained, so how we get the results. So we included all the relevant cosmic ray interactions. So the major contribution, or you can say the background flux, came from proton-proton interactions and cosmic ray interaction with the CMB. So, and this is the most detailed method until now. Nobody haven't used the way we like we use the 3D MIT simulation and a cosmic ray propagation, considering that 3D MHD simulation as well. So it's like when we estimated that and it was high from these models, we were a little worried at that point as well. And then I cross-checked with my models and the interactions we are considering. So I would say that's what we get. And like, okay, so the attenuation effect may come during the cascade due to EBL or due to EBL or CMB. And okay, in case of EBL, that cascading effect or the attenuation effect only important in the high energy range. And the major contribution in our results came from the low redshift range. So I would say that attenuation effect due to EBL is also not important, like at least because the major contribution coming from the low redshift range. So this is my, like, you can say, like my explanation that we get, like how we get, I explain, like we use the simulation and everything. This is how we get. So and if somebody did that analysis, I would say no. Nobody haven't done yet. Like considering completely the MIT simulation and also the propagation effect, like cascading. So this is what we get finally. So
yeah, but I think the detailed simulations actually not affect actually essentially the basically the because for example if you just assume the power laws, then basically I still expect that this kind of attenuation curve. It's a kind of this is generic. As long as I study because for the wide parameter space or the redshift evolutions, I still have find this kind of. We also I think the previous studies I consider mass function too, right? They also take into account the addition of the ultra-high cosmic propagation, but the shape does not change, and that's the reason why I asked this question in my first question, because the reason why I asked dn over dm is actually the best because because as long as I study use the non-redshift evolution or a bit weaker evolution, the basically still actually it follows. I don't get this kind of flat curve. So then the only reason I came up with actually is maybe the effective evolution is stronger than the what was obtained in the previous literature, and that's the reason why I asked about dn over dm, the mass function. Then that's the reason why I asked that whether you made a detailed comparison between the results of the MHD simulation with the mass function result used in the previous literature.
Okay, I think an important, if I may make a comment, an important clue from these comparisons come from the results, for instance, from Zandanel et al., right? Because they get this flat spectrum as well. And the reason is that
they don't because they don't consider this. Just they want to give the estimates, just to get the flux level. So it's not it's quite misleading to use this curve for the spectrum comparison. So but for the spectrum comparison, I think that this kind of shape is quite stable. I think of course, if you consider this, actually the shape is actually simply because the cascade spec is almost universal for the right, because then you can actually, and then of course there's some effect due to the evolution, because if you consider weaker evolution, there's some local sources start to contribute, but still for the wide parameter space, the shape is actually something like that. So if you have such a hard spectrum, especially the 10 TeV range, in this case, I think this is possible only if some source. There are many sources actually which actually much less than the zero redshift, probably 100 megaparsec or dozens of few hundred megaparsec are super important. But that is why. But in this case, I'm kind of start to wonder that this mass function is actually maybe different from the
right. Yes, so, definitely. This is the distribution function. Yes, the mass function distribution is
namely if it's the -2 and then just weak evolution, or TD like bit weak evolutions. Actually, for example, we also consider accretion shock model, right? Accretion shock model is actually the negative kinds of relatively weak evolution, a bit weaker than the non-redshift evolution. Even in that case, I still have such a kind of shape, so the universal shape. We didn't get such a flat curve. So that it's probably kind of. It will be useful to make a more detailed comparison of why you had such an excess emission.
Right.
I mean, but so looking at the individual source, again, can the non-detections of individual cluster sources from the current gamma ray experiments help us understand the discrepancy, in the sense that, well, at least from an individual object, you can put better constraints on what you expect from the population, especially at these very high energies, or it's not really constraining.
Can you repeat your question? If you like, so if we consider the individual sources and Can you?
Yes, where you consider the expected flux from an individual source, from observations. I mean, we have not detected any clustering in the gamma ray range at these energies yet.
Yes.
So this puts a strong limit on the maximum flux of individual sources in the gamma rays. So can these known detections put some limits on the expectations that can add to the results of your simulations, and then help this discussion to understand better this flat curve that you have, and if it holds, for example, against observations at the moment, or not really, because the flux of the individual sources wouldn't put much constraint there.
Yeah, I don't think so, because I show the contribution from individual. So they are so you can say we don't have, and in case of diffuse gamma ray we don't have detection like in this range. So I don't think they are like, you can say that way, that the lack of detection, so the cluster may contribute in that energy range, but yeah, that's the only thing one can say.
Okay. Yes, because it's so much higher than that. I was wondering if it would have an implication for what one expects for the flux of the individual source, yes, of a given cluster. That was the.
Yeah, I agree with this comment. Actually, it's probably important to check, for example, using the same model, it's very important to check the flux expected coma clusters. For example, actually the Nishiwaketo is a kind of this estimate is actually based on you can make the opposite argument, right? Yeah. So because coma clusters, we already have a very strong limits on the gamma ray flux. So then, in order to not violate the coma clusters, actually there's some possible claim, but which actually you don't have to trust. But anyway, based on these upper limits, actually you can estimate the diffuse flux, in the which is consistent with the upper limits placed on the individual clusters nearby object, right? And then basically the Nishiwaketo estimate is based on this actually the estimate. Of course, this is still the model dependence, but it's actually this is a kind of important question. You also have a similar prediction, right? So using the same model, if you take this model, of course, if you calculate the gamma ray flux in nearby clusters, this expected gamma ray flux should not violate coma clusters. For example, the Virgo or coma that we have actually strong limits.
Yeah, it's exactly that. I mean, and one of the reasons I was asking this question is because I know that Bete and your group, Saqib, you are also members of the Astro Mini Array, and the Astro Mini Array is going to be a new array. It's going to be built. Correct me, Bete, but I think within the next 2 or 3 years. And it has a very interesting science strategy. I mean, since it's a precursor to CTA, it has decided to dedicate a lot of time to observing key sources, up to 200 or 300 hours of integration, deep observations in the direction of a few sources, which is something that CTA will never do. CTA may spend 50 hours in a very interesting source, may spend 100 hours or 200 hours in the galactic center, but will never spend 200, 300 hours in any source apart from that. So you have the possibility of really taking very interesting deep data on these kinds of objects like the coma cluster with the Astro Mini Array within the range of the next 5 years, let's say. And this could really help to put limits on these kinds of studies. And so I missed in the thesis some mention of the implications that your predictions or your study have, for example, to directing the science case of an observatory like the Astro Mini Array, which is going to have a lot of flexibility for derivation of the science program, and of which you are a member. So I don't know. Have you considered applying? I mean, the implications.
Yeah. Okay. Yeah, that can be done. Okay. So in this thesis, we only focus, like, you can say, the total flux from the whole population and neutrinos and gamma rays. Okay. We can study like using the same, actually, the tools to study the individual cluster like Coma, Perseus in detail, like as Nishivaki actually did. They did for the Coma cluster, but you can constrain if you have a background simulation even better. So like we have planned for that. And I don't know if I'm mistaken, Betty has even a student working on that already to in that direction starting. So in my thesis, okay, I do calculated the fluxes for the individual sources, but you see, it's just we probe only the high energy and then using that like cluster of different masses and calculate the total. So we haven't studied in detail a single clusters with like with different acceleration scenario or the cosmic ray propagation and everything. So we have a plan for that, yeah. And it's like, and it will be not like that difficult, or it will be quite easy since we already developed like these simulation module or something, and then it will be easy to study that.
Can I make an extra comment on this? Yes, actually, the science case of the Astro Mini Array, it is ready, right? But there is room for other studies. Just that, you know, we do not have, I mean, within the collaboration, systematic plan for many hours of observation of clusters, right? But of course we are going to fight for, in the sense that, okay, eventually we may include this, but we have just submitted the science case paper for Astri, and this was based on studies performed over the last 4 years or so, and with upgrades for the last site, that is Tenerife, and of course we did not had these studies ready when all these simulations were being, I mean, the tests for the tools, the targets, not the tools, but the targets for the main targets for the Astro Mini Array for the next few years, right? But of course there is room for this sort of studies, and it's straightforward because we also have the sensitivity curve. We know what we might expect, and to do this evaluation and see if we can get some signal from there, it is something that is in our minds as well. Now, regarding this flatness, yes, this flatness was, as Saqib commented, was also a surprise for us. So we cross-checked many times, but what Kohta, the points that Kohta mentioned can make a difference. So, for instance, we may compare this mass distribution function with observations and see whether we are missing something from the simulations. Because of course, when you also integrate the mass distribution from the simulations, you take these, you integrate over volume portions of the system, and there is always the possibility that we missed some point. I don't think so, but definitely this is something worth exploring, right? All we know is that we see from these detailed simulations with this, let's say, more complete background distribution across the redshifts, we do this trend for this flatness, for this flat spectrum, and of course we have to understand if this is real or not, right? So Let's see.
Yes, thanks. So another point, and I don't have that many questions. I mean, as I said, there was a lot of discussion previously. So it was discussed and it was kind of explained the reasons why when you compare your neutrino results with Feng and Olinto, you have this difference in the range of redshift that dominates. So my question is again trying to bring to the observational side. So is this difference in the expected redshift that contributes the most to the kind of background neutrino flux sufficient for you to be able to test with IceCube or KM3net the difference between the two models, in the sense that you would expect some spatial signature, for example, from your result, which indicates most nearby clusters, or the redshift range is such that the distribution would be already homogeneous, and you wouldn't have. I mean, I think that 0.01 redshift, well, 0.3 is quite far already. So probably the distribution of clusters then is already homogeneous. Yeah. So maybe there is no spatial signature, but it's just a curiosity, you know. Or if the flux could be so intense for individual sources again, that from the closest ones, if they dominate, you could again expect some accumulation, and that could be tested from a certain direction with IceCube. So again, looking at the observational side.
Yeah, so as you, okay, because this is a large redshift range, like 0.3, so it's gonna be, again, the population gonna be homogeneous. So, yeah. and also the difference is not like you can say that much. It's almost in the same, as you can see. I think I'm already showing the slide. So I don't think so, like with the IceCube, and if the individual sources are already dominant, so cannot do.
Yeah, no, it makes sense to me. Yes, it's difference are not so much, and 0.3 is not that close by.
Yes,
I agree. So,
well, can I give a comment? Yeah, but yes. I think that's still important. I think that if you only look at the spectrum, may not be, but this affects anisotropy. And actually, if you have local sources, actually, you have more. For example, in order to give for given diffuse flux, right? So if the evolution is strong, and most of the sources actually that are located at higher redshift, actually, you have less multibreadth or less anisotropy. And if you have actually the more local sources, actually, it gives a more doublettes or multibreadth and more larger anisotropy. I think anisotropy information is actually already gives a constraint. And for example,
you think the constraint would be sizable then, or potentially?
Actually, already this galaxy cluster accretion zero data shift evolution model is actually already constrained.
Okay.
Even now, actually, it's already intention. This is actually shown in my paper with Eli Waxman. So the accretion model itself is actually already constrained. In order to avoid this constraint, you have to actually have a stronger evolution. So basically, the accretion shock model is already in tension with the anisotropy data.
Okay, so maybe, I mean, given this comment from Kohta now, maybe this is something that would be interesting to include in the discussion of this point, because, I mean, when you have clear discrepancies between models, it's always good to point out if there is any experimental data that can point to a resolution between the two. So I guess to mention this reference that Kohta said and to comment on this could improve the work in this section.
Yeah, that's interesting. I will.
Kohta, and it's Waxman, Murase. Which year is that?
2016.
2016.
Okay. Yeah, so we actually discuss a constraint which can be priced of the absence of the multibreadth event, and basically it's caused by anisotropy information in the neutrino sky, and then basically the weakly evolving sources are more strongly constrained. So in this sense, actually, it's difficult to exclude because the model uncertainty is large, and but its intention with the data already.
No, very good. So I guess this was most of my specific questions. As I said, I didn't want to add that much and would focus more on the experimental side. But I would have to give some general comments. So first of all, I would, I mean, it would be good to go over the text again, Saqib, and look for some typos. I marked someone and I can send to you. But for example, there were some things where I think that signals of saying, for example, significant suppression in flux of cosmic rays above 10 to the 17, where I think it was below 10 to the 17. And so there are some inversions in inequalities when you are defining ranges, which are clearly typos. So I marked them, or maybe I didn't understand, but I will send that to you later. And one thing, right in the abstract, I mean, and this is, I just picked that because it was right in the abstract. You say that, of course, these multi-messengers, the neutrinos, the cosmic rays, and the gammas, they have a common origin, and with this work you can test that they have a common origin. I mean, we know that they have a common origin in the sense that the process that produce one of them will inevitably produce the others in the case of hadronic process. So they are connected, and this is very understood. Perhaps the way I would put that is the emphasis not on the connection between the messengers, but the connection between the messengers within an astrophysical environment, for example, the clusters. So that so I would emphasize that because then this gives, I guess, better emphasis to what is really relevant for the work, because simply the connection between the messengers is rather generic. And then the introduction as a question of style, but what I would do differently is that you go in a very long sequence of text. But perhaps if you add subsections, you can organize the text better. And it's simpler for someone to go back and look for the points that he's interested in the text, in the introduction. So whenever I wanted to go back to your introduction, I was looking around, and it was a continuous text. I think there is only one subsection. But if you can break that a bit more, I guess it facilitates the readability. So I would suggest that.
Okay, thank you.
And then the other thing that I would suggest, which I think was touched upon by Rafael, is that in the conclusion, you could perhaps, I mean, you make a very broad conclusion in the sense of what can be done generically in the field and as a continuation of this work. But if you could point out where you want to go, so what is your next plans, and what exactly do you think your work opens up as a window for future research, that would be very interesting as well. So I was missing a bit of that. So maybe you can add a paragraph or two, really focusing on the implications of your work and not the more generic prospects for the future of the field. It's good to have both, but if you could give some emphasis on yours at some point as well.
Yeah, that will be really great. Yeah, I will take that point.
So, and just then a very simple one in figure 5.4 in the legend, there is a mention to a bottom panel, but there is no bottom panel in that figure. It's only one panel. So
okay,
that's easy because it's a figure. So
I know.
That's an easy one to point out. It's figure 5.4.
Okay.
But the other typos and things like this that I caught, I'm going to send you by email, and then you can correct.
Oh, thank you for the very nice review of my thing.
And then I have a question. I don't know actually if it's a curiosity.
Okay.
So when you are dealing with hadronic process in this cluster environments, of course, secondary electrons, which are non-thermal electrons, are going to be produced as a result of charged pion decay. So I'm not an X-ray astronomer, so maybe, I don't know, Gastão here will be able to answer that better than me or other people. But I was curious to know if this population of secondary non-thermal electrons would give us observable signal in the X-rays in the clusters or not. This would be very hard X-rays, I suppose. But in the midst of all the thermal emission, it was not clear for me if it would be visible, if it's interesting. But it's a curiosity. So,
okay, if they are electrons, so I think they can produce hard X-rays because they're in the magnetic field. So they will lose energy and produce photons. And yeah, so we didn't check what can be the spectrum or like what can be. So I don't know, but like
yes, I mean, what I wonder is if there is a characteristic energy signature, and if the density of these electrons is high enough so that it would be sizable compared to the other X-ray components, and maybe the spatial distribution of these electrons could be interesting as well. But this is, as I said, is a total curiosity. Is an extra thing that came to my mind. I don't know.
Yeah, it's also until now it's also a curiosity for me because we haven't studied that. Okay, so you can model or you can say calculate the population of neutrinos which will produce as we calculate the neutrinos, and then further like study their interaction with the background and see what kind of photons they can produce. So that can be done. Like this is and it's also, I don't know, in clusters, if you consider like primary dominant model or secondary dominant model, like electrons are being injected in the cosmic rays as a result of hadronic interaction, or like they are accelerated as the cosmic ray, the protons are accelerated. So that's also like one of the study like we can do or like interested in.
I think
Can I comment on this? Okay, no, go ahead, Kohta.
Yeah, I think that should be. It's kind of interesting question. Then one of the studies actually includes the Nishiwakators, and usually I think that this is a very important check in the radio data, because in understanding that usually the radio constraints are stronger.
Okay.
And then some people actually try to use a secondary electron to explain the radio data. But usually the people believe that it's a bit tricky, that in a sense, if you want to explain the radio data only with secondaries which are cooled by passively, it has difficulties. And people actually, they introduce effect of deaccelerations. And basically, if you secondary electrons which are injected by the hadronic interactions are reaccelerated by turbulence, and you can actually modification of the spectrum that you can explain the radio data. Then you are right. In principle, you can actually have also prediction for the X-ray flux. But as far as we study, it's not so easy to detect. This is actually probably depends on the magnetic fields you consider. At least if you consider halo regions, the magnetic fields are strong, and in this case, actually the radio data is actually stronger. And then the X-ray flux is in the comma case. Actually, it's order of the 10⁻14 percentage cubic per second, minus 10⁻14. And then it is difficult to reach with plan, the future X-ray telescopes in the hard X-rays. But I think that actually is in principle it has a room to investigate, especially if you start to consider the other regions of the accretion of the cluster. And then in their case, they have a simulation. In principle, they can resolve the actual region of the shocks, right? So then it's possible to compute the contribution of the both X-rays and both of the primary electrons and the primary contribution of both secondaries and primary electrons.
Thanks, Kohta. And so just to complement then, so at least from the side of the radio, is this measurement potentially effective in constraining the cosmic ray?
Yes, I think so. I think that's actually this is actually related to the Zandaner et al. So in principle, the Saqib simulations actually you can you can compute the prediction for the radio data, and then maybe the radio data is actually can be checked. Radio change can be confronted with the data. Especially, for example, that you can do this for comma. But the one caveat is that you can always make the story complicated, right? Because as I told you, that now people believe that the acceleration may be important. And then in that case, okay, it may not be simple to make a direct comparison once you start to include additional effect.
Yeah, just a comment because I was commenting on this, but Kohta gave a very complete answer and a phenomenological answer to this one. But in principle, from the simulations with the cosmic ray cascading, you can get the entire spectrum and the non-thermal spectrum, but the spectral energy distribution in all wavelengths. But again, this will give you a clue on this non-thermal part, for instance, for X-rays, that is you have to compare with the thermal Bremsstrahlung contribution, the whole thermal Bremsstrahlung contribution. This would be a secondary effect. With regard to the low energy, the radio, as I think Kohta completed the answer by Kohta is rather complete, and then of course that's it. Now I have just a comment with regard to the paper of Waxman and Murase, because this is included in the thesis, and it is quoted in the Saqib's thesis and also in the neutrino paper. So it's already there. This we put this in this prospect as well, right? So it has been put in this prospect as well, because this work has been mentioned in the neutrino paper and in the thesis in the neutrino chapter. So Ulisses, do you have any further comments or questions?
No, that was all. Thanks.
Okay. Thanks a lot, Ulisses. All your feedback, your input, your questions and comments on the thesis, all these are very welcome and very important. So thanks for this feedback as well. So let's move to the nearest people. So Gastão, please, can you make your inquiries?
Yes, I can. Thank you, Betty. I didn't want to jump on this discussion about the X-rays when Ulisses started. Then Kohta answered, and Elisabete also made some comments. But just to add that the capability that we have nowadays to detect X-rays are quite limited. We have very good satellites still operating, but they go up to 10 kiloelectron volts only. So the contribution of non-thermal electrons is beyond that, where we have very low resolution, very low equivalent area, so low sensibility. So it's very, very difficult to detect X-ray flux from clusters of galaxies in the range that is interesting here, that's above some tens of kiloelectron volts. So going back to what I want to say here, first of all, after over 2 hours of discussions, almost everything is covered, and I have only a few doubts that I had reading this thesis and listening to the presentation. And Saqib, you don't have a copy of your thesis with you? You cannot open a PDF?
Okay, so yeah. Just give me like 2 minutes, I'll open it.
It would be easier, I think, because
Yeah,
we had already some references to figures.
Can I connect my USB here to connect my thesis or something? Should I send you?
Yes. Do you have it?
In USB.
I think this is the first time I see someone going to a conference without the thesis.
That's true indeed, because nowadays nobody prints out, and then I think he forgot to bring his.
You don't have to print, but at least have the PDF available.
Yeah, the laptop. I think he forgot to bring the laptop with him to the conference room. Yes, this is really. I mean, I would feel very comfortable with my thesis by my side.
Without what?
Maybe it would be easier to download from email.
Saqib, you don't have to. You are downloading it, okay? Because you do not need to open it just to us. You open to yourself, but.
No, I know. It's like because I'm.
I think it's faster if you go and get your laptop.
No, it's okay. No trouble. Forget about that. Is that? It's just that my questions is very. It's more detailed, so it is easier pointing in the text.
Manda pelo seu próprio e-mail, tá bom?
Yeah.
Você tem o seu e-mail, né? Vou fazer isso aqui,
ó.
Tem aqui isso aqui, bom.
But let me send you.
Aqui, ó, tá seu e-mail aqui, ó.
But it's not in my email.
Tá no Drive?
No.
Saqib, you sent the copy to all members. The last version to all members by email. Do you remember this? You may look for one of those emails.
My email is not working there, so what can be?
You want me to send you a copy right now?
Listen, maybe we go on and forget about that.
Yeah, my computer is not working. You have something you can connect my USB, or it's not working?
No.
Did it work in your computer?
No, my computer is not working actually.
Saqib, ó, tá aqui, ó, seu e-mail nesse computador. Só baixa a sua tese para esse computador aqui, ó. Já tá aqui, ó, seu e-mail. Esse é seu inbox.
I don't know where it is.
Eu vou abrir aqui, ó, para você, ó. Só vai lá, só passa o mouse para essa tela aí. Pega ela aí,
Saqib,
baixa ela nesse computador.
Saqib, try one of the emails that you sent to the board.
Yeah, that's what I'm going to do.
Do you want me to send you a copy again?
I think that's not the problem.
Yeah,
We just got it.
I opened.
Okay.
Yeah, you can open or you can download it.
Yes, I'm going to download it here. So
Yes, download it.
okay.
Now you can.
Then pasta, deixar isso aqui. Aí vou compartilhar de novo. Ó, você coloca de novo aqui. Cadê eu abrir com reader, aí Ctrl N.
No, do Control N.
Ah, tá. Bom, só fechar isso aqui.
Yeah.
Nice.
So,
thank you. Okay, so actually my first question, I don't even need to point to a page, but it's at the beginning of the introduction. So the question is a very basic one, because something that I don't quite understand and didn't understand reading the text. But there's some things that we often write and we often read in text about cosmic rays.
Mm-hmm.
And so you say that particles can be, charged particles can be accelerated in the front shock in clusters. So you have a shock wave moving in a cluster, and that can accelerate clusters. That I can visualize that, and I can quite understand. But my question is, how can turbulence accelerated charged particles to very high energy?
So the turbulence can cause, like you can say, produce these shock waves, and then further they can be accelerated. This is.
Yes, let me explain what's my doubt.
Mm-hmm.
Is that when you have, for instance, a merger,
Mm-hmm.
a group or two clusters merging, then you have a strong front shock wave moving around.
Mm-hmm.
And that's it's quite another, you have a kind of a boat motion. But when we talk about turbulence, I visualize that as a more chaotic movement and in something that goes down from large scale to small scales. So you have a mixture of things going on. And that's why I have this doubt. How can this situation produce the large acceleration of cosmic rays? I mean, wouldn't that kind of cancel the acceleration, this chaotic motion over a large range of scales?
Yeah, this is, you can say, like, okay, it can happen as well, but to create shock waves or like in the structure, so there will be some like turbulence or whatever that will create that shock, that will initiate that instability, and then it will grow. So this is like how you can say the shock form, and it will further produce, can accelerate cosmic rays.
Saqib, please remember that there is a stochastic second-order Fermi acceleration as well. You have this second-order Fermi acceleration process in pure turbulent environments. Of course, behind shocks, you also have turbulence that we allow for the particles trapped in the shock to suffer mostly head-on collisions with the magnetic fluctuations, and then they get this stochastic, more first-order Fermi acceleration. But in pure turbulent environments, you also have a stochastic Fermi process. Actually, Fermi proposed the second-order process. He was inspired by turbulence, by distribution of clouds, magnetized clouds in the interstellar medium. So it's a stochastic process that allows for particles to suffer head-on and receding collisions. And Gastão, so you are right when you say, oh, this would cancel statistically the process. Actually not. You can demonstrate that the frequency of head-on collisions is not canceled by the frequency of receding collisions. And that at the end, you have a second-order effect where particles get an increase in the energy that is proportional to the square root, to the square of the velocity of the colliding fluctuations or clouds divided by c. So it's stochastic. It's a stochastic process that allows for a net increase of energy of the particles that is less effective than particles being trapped behind shocks, because this stochastic process is more a first order Fermi process, but in pure turbulent environments, there is also acceleration. And this is actually because you have also reconnection in turbulent flows. Reconnection improves the process of acceleration, this stochasticity, and instead of having this dependence of energy increment with the second power of V over C, where V is the colliding structures that are interacting with the particles, you have something between 1 and 2 that is 1.5 or something like that, because of the presence of reconnection that also improves and allows for this stochasticity of the process.
Okay. Okay, thank you, Betty. If you were the candidate, it would be a very, very nice answer.
That's why I added, because Saqib knows this, the Fermi process.
Yeah,
I don't know
that's why
why.
I wish I heard it from him. I'd rather hear from him that, but it's okay. So going on. So let's also something that I didn't know about. It may be some basic physics. It's on page 14 or page 14 is what's written. Not on the PDF is page 42, and it's about. There's a phrase here that says the back reaction of the field based on Maxwell tensor, and what's this back reaction of the field based on Maxwell tensor means? So on page 14. No. It's you. Yeah, go back.
Page 14.
Yes.
On PDF.
No. That's written on the page. The number written on the page. You are at 26 here, so it's 14. It's up. Yeah, right. 19.
Yeah, this here.
Right.
This
in
one.
The first paragraph, right in the middle of the first paragraph.
This one, magnetic balance back reaction of the field. So that's based on the like the MHD simulation. So these are when you include the magnetic field effects in the plasma. So like in hydrodynamic plasma. So we give the detail in the appendices. So how we like calculate this and what does it actually mean. So the Maxwell tensor is actually if the magnetic field effects on the plasma, how you can calculate it. So I don't know if I can go to the appendix if you want to see how we calculate that.
No, it's okay. Okay, let me see what I have here. Yes, that's it's a real curiosity that I have. But somewhere in section 2, it's the same section, and you define the overdensity in terms of the baryonic density.
Yeah.
It's in page 18.
Okay.
You say the overdensity in figure 2.5 is defined as delta, and but you define in terms of the baryonic density, and it's for me it's quite unusual that. So my question is that the usual way that you see that definition? If for you it's the normal definition. I know that different communities have different ways of doing things. And but for me, overdensity is always defined with respect to the total density, not the baryonic density.
Okay.
So I wonder if this is a typo or this is how you do things.
No, it's actually defined by the like in the background MHD simulations how, and that simulation also performed by Dolag et al. That was one of the member. I couldn't make it, So it's defined in their ways. So I put it as it is because I'm using that simulation exactly. So
Okay.
the background image simulation, yeah.
But it's for me, it's quite surprising to see that's kind of the definition based on the baryonic matter, but it's okay if you do that. Now, I had something noted somewhere. It's how do I put that? I have another comment. Is about what you call clusters. As I said, the different communities certainly have different ways of expressing things. And during all your thesis and your presentation, you call this collapsed structures as clusters. You say the clusters, and then you give the mass range of clusters going from 10 to 12 to 10 to a few 10 to 15. And that's quite surprising because as far as I know, or I remember, I think I never read someone refer to a 10 to 12 solar mass system as a cluster. And I never heard that. Usually, we start to call clusters structures that have masses above 10 to 14. Above 10 to 14, we call that clusters. Below 10 to 14, we call galaxy groups. There's that's a convention I'm used. But below 10 to 13, I never heard people referring to those structures as clusters.
Okay.
So, is that normal for you to call 10 to 12 solar mass systems as clusters?
So 10 to 12 is okay. It's a lower limit, and in the literature, in the high energy gamma rays, you usually find that people like they even calculate the contribution of clusters whose mass is around 10 to the power 13 or around 13. So, and 10 to the power 12 solar mass cluster is like their density is quite low, and you only find these clusters at very high redshift. Okay, in the simulation we find structures, so that you can suppose is a cluster, or you can say a group of galaxies. But in the literature, they probe the mass range of the clusters. So in that range, as I don't know if you see my in the neutrino contribution, we show the flux from Fang and Olinto, and they also consider that range. So I suppose, and there are some other works as well, at least Fang and Olinto, I plot their flux along with mine. So they kind of show that.
Yeah, but I think that I agree with the Gastão. I think basically people use that. Actually, we usually say the galaxy cluster group model. Then because the galaxy cluster is actually used for the halo mass larger than 10 to 14. And then the 10 to 13 to 10 to 14 that we call groups. And then we usually consider only for the contributions only above 10 to 13. Then because below 10 to 13, yes, in this case usually attributed to galaxies, right? Massive galaxies. And then then we usually say the galaxy cluster group scenario. If the contribution from 10 to 13 to 14 is actually important. Then you can also take into account the contribution below the 10 to the 13. But in this case, usually this kind of halo mass attributes to galaxies. Probably the physics you are applying might not be complicated by the effects of the galaxy itself, right? Because in this case, you already consider halo, but in this case, you have disk and then you have feedback.
Yeah.
Okay.
Yeah, the star formation and everything.
Yeah, that is why usually in the paper, actually usually people put some cutoff in the low mass and run 10 to 13, which is actually correct, actually more or less a range of the galaxy groups range.
Mm-hmm. And Yes. What I think also, as Saqib said, they did the work. They considered all this mass range. So I think the word you are looking for is dark matter halo or halo. Or matter halo, whatever, because that's a generic term, and that's used a lot in antibody simulations, cosmological simulations, and it refers to anything that has collapsed. So when you talk about dark matter halo, it can be associated with a cluster if it's very massive. It could represent plus a group of galaxies, and even a single galaxy with a few satellites. So I'm saying this because it's a bit confusing when you expected some terminology and then people use another one. And sometimes you can make a wrong idea about what you are saying. So that's just it's more a suggestion, it's a minor point. So now I have another question. So I think it's a typo. It's in a little bit further. When you describe the density profile in clusters, you talk about the beta model, and then you give a typical beta value, 0.8, a core radius, and that's okay. But then, yes, that's the page. And then you talk about the central density, and you quote a value of the central density of 10 to 5 centimeters minus 3. And am I reading that correctly? Is this 10 to 5 the central density that you used for the 10 to 15 solar mass cluster?
Because the maximum density can be 10 to the power minus 2. So,
right. Yeah.
Yeah. This is a typo. Exactly.
Okay. Okay. If it's a typo, it's okay.
Yeah.
So you better correct that also.
Yeah. Thank you for pointing out.
So okay. Well, there's the. This was discussed already, the figure 2.7. I'm just looking what I marked here. Oh, you said that, yes, I have this question is, okay, so you have the simulations. So you have the clusters in your simulations. So in these clusters, you have some dark matter, you have the gas. But my question is, how do you relate the cluster mass with the Bremsstrahlung photon fields? I mean, because you don't have the Bremsstrahlung photon field directly from the simulation. So you have to assume something. You have to do something.
So you calculate the energy from, you know the temperature actually. So from temperature, you calculate the photon field.
Just that. You take the temperature and the density, and then you compute the Bremsstrahlung emission.
Yeah, because you have so you have a temperature and density, and so what I did, so I divide the cluster into many spherical shells. So I divide into a first one, and then you average out the temperature and correspond to that temperature and that number density. So you have a formula from which you can, by you applying that, actually it's an integration over the whole frequency range, and from which you can calculate the photon fields.
Okay, that formula that you referred to, it's a simplification. I mean, it's a simplified way of how the real cluster emits. I mean, there's you wrote, I think that you.
Yeah, I wrote that formula.
Sorry?
I wrote that formula, chapter 3. I'm going there.
Yeah, it's written somewhere.
Yeah.
But my question is not really about the formula, but it's about the X-ray emission in clusters. You don't have only the bremsstrahlung emitting the soft X-rays and even a few % of the hard X-rays. You have also line emission. You have the emission produced by the ions in the gas. So you are neglecting that. And my question is that wouldn't that be important to take into account or not? Or it's completely negligible?
Okay, so we haven't studied that, as already Kohta suggested some, like we should consider that those other photon field possible. But yeah, that we haven't studied that if it's maybe important or not. And I don't know, because here we mainly focused on the total flux from the entire population. So for that you have to study, like you can, let's say, one cluster in detail with all the aspects. So then like that can be done, or that's our plan as well. So but yes, we didn't study that in detail. Yeah.
Okay. Yeah. I mean, if you are going to low mass clusters, low mass to groups of galaxies, line emission is almost or even as important as the bremsstrahlung emission. It's very important. You'll have a lot of photons there. So, but I don't know if it's would be important because they are at low energy. Anyway, now I have another question. It's well, let me jump ahead. It's a figure 4.5. It's in page 68. It's really a curiosity. It's something that I tried to understand, but I couldn't.
Figure what, 4 point?
Figure 4.5, page 68.
4.5.
Yeah, that's the one. It's looking at this figure. It struck me that you have you are going down in mass. So from 10 to 15, then 5 10 to 14, 10 to 14, 7 10 to 13, and I would have expected that the curves would be more or less equally spaced, or at least separated one from the other. But what I see there is like you have a bimodal, a kind of bimodal situation. You have two curves almost overlapping at the top, and two curves almost overlapping at the bottom. And why is that? Why you have this kind of bimodal situation?
Okay, so that's okay. So we calculate the redshift of the neutrino if when they arrive at the edge of the cluster, and this is the average redshift per energy bin you get, and for more massive clusters, and this is completely is not propagated up to the Earth, or the flux is calculated at the edge, and so for let's say massive clusters, so their redshift is, if you average out, they are almost the same, but okay, like in the high energy range. So because here in this figure the statistics is not enough, like the number of particles we are considering. If you consider like large statistics for large number of particles and measure that quantity, so that's like it should be almost the same every for all the clusters. So here this behavior is you can say is bit like not simplified, when you say like you smooth somehow, but the statistics is not enough. So the bimodality is just due to like you can say lack of statistics. So if you have more number of events, so then the result should be the same for all the clusters, especially at least for the more massive, and the curve even should not like that much like bulby, or it should be straight. So in these results, I might say like we have to improve the the results in this case.
Yeah, okay. Not certain I understood, but okay. So I have one last question. It's also a detail. It's you said that during your presentation, you showed the figure. I don't remember. I think it's figure 5.8.
5.8.
But I didn't have the page here.
If you know the figure number is right, then I can go.
5.8.
Okay, then I can go. Yeah.
Let me see if it's that.
5.8.
Yes, that's it. And yes,
Yeah,
in your presentation, you point out that you have this this gas density correction. And well, what exactly is this gas density correction?
It is due to because our simulation is non-radiative, it's not considering any AGN feedback or star formation inside the cluster.
Okay.
So if we consider that, then the gas density will reduce. So if gas density will reduce, then the cosmic ray interactions, because the gas density reduced, then the proton-proton interaction will be less, and consequently there will be less production of secondary particles like gamma rays and neutrinos. Here I'm showing for gamma rays. That's what
I'm sorry, I didn't understand. You said, of course, you don't have emission on this in the simulations. That's okay.
Yeah.
But then I'm not quite understanding what's this gas reduction. Why you have to reduce the gas on your simulation?
Because
what are you correcting actually?
So it's like, okay, so our simulation doesn't consider that. So to include that effect, so we use this figure, actually this one.
But what's this?
So this figure is actually showing like as a function of mass, like gas fraction over this one. So you can see for low mass clusters, there can be more star formation or AGN feedback, and the gas density is decreasing. But for the high mass clusters, it's not. It's okay. It is increasing. So it means because we are considering cluster of different masses, so they are producing a certain amount of gamma ray and neutrino flux, and the main interaction which is producing that flux is due to proton-proton interactions. But if we consider the star formation or AGN feedback, then the gas density will reduce, because it will be used in the gas star formation. So, and then there will be a less gas, or density of the gas will be less to interact with the cosmic rays, and consequently there will be less secondary particle production. Okay, we haven't considered as it should be considered in the MHD simulation. We use these results and empirically find or quantitatively find that if a mass range is between 10 to the power 12 to 13, then that reduction will be that much, like it will be more noticeable, and then for the heavy mass clusters.
Okay, so what you're saying is that in your simulation, you have a certain quantity of gas, and since you are not taking into account the cooling, then you are not depleting this gas in lower mass systems, in groups of galaxies, which will be forming stars or whatever.
Yeah.
And okay, so you are correcting for this trend in the gas fraction. Okay.
And can I add a comment on this?
Sure.
The physical reason of this depletion. The main physical reason of this depletion is that star formation and the AGN allows for the production of outflows that expel part of the gas to outside, and then you might expect this decrease in the density distribution because the gas expands outside. So it's essentially this that you see in the other curve, and this decrease it's only a factor of 2 or so.
Okay. Okay, good. So, okay, so I'm satisfied. As a final comment, there's something that I missed in the presentation and also in the text. It was a more pedagogical approach, let's say a more something more easy for the rest of us to understand the big picture, like putting this thesis, this work, which is very interesting, connecting this all these messengers, the neutrinos, cosmic rays, and gamma rays, gamma radiation. But for me, since I'm not a specialist on any of this, I missed some, some pedagogical introduction, something that goes from first principles and the big picture, and then you go deep in your work. That was something that I missed, and but otherwise it's a very interesting work, and I think that's full of potential for the new instrumentation that are being developed and things that we'll see in the next few years. So thanks again, and I finish here.
Thank you.
Gastão, thanks a lot for your input, your comments and questions, and of course they will be taken into account as well. And now let's move to the last reviewer, Reinaldo Santos Lima. Please go ahead.
It's muted.
We cannot hear you. No, we cannot
It's
hear
muted.
you.
Sorry.
Okay.
Well, thank you, Saqib and Betty, for inviting me to be here in this committee. And I'm happy I had the opportunity to see the conclusion. This work I have been following as the referee report of Saqib since the beginning of this work. And congratulations, Saqib, for the work and for the test and for the results. I think they are very interesting and relevant. I think a lot was discussed here. We had opportunity to discuss a lot in the last years, but I still have some doubts, some comments, and at some points in the thesis, I think they deserve more clarification. I will send you my comments, the typos and some small comments I made in the thesis to you, but I'd like to use some time here also to point you at some points I think need more clarification. So it's good that you have the thesis there projected. Some of my doubts were already solved by the questions by the colleagues. For example, if you go to page 19 of the thesis, is the PDF page 47.
47?
In the PDF is 47.
Okay.
It's the
47, yeah. Here? Yeah, this one, yeah.
Yeah, so it's 47 of the PDF.
Yeah, this is 47 of the PDF.
Sorry, of the file. The file. In the thesis is 19.
19, okay.
Yeah.
19.
So this is related to also some of the points that Gastão mentioned. So you go to the upper plots, they have some cuts with the density, but these numbers, of the density, they do not make sense. And I think along the thesis, several times the density, the numbers are a bit strange. I think you could check. For example, there, this number is grams per cubic centimeters, 10 to 8. I think is you see they do not make sense.
It's 10 to in the density.
Yes.
It's over density, so it's 2 into 10 to the power 5.
Yes, in the first line, so 2 times 10 to 8. So
it's 8
yeah,
or 5?
I think it's the over density.
Yes,
dimensionless over density. But in several points in the text, it appears as density as grams per cubic centimeters. But it's good to check all these units of the densities. Where I found, I pointed you, so you could solve this.
But this is 2 into 10 to the power 5, not 8. Yeah?
Yes, even so. Yes, so it should be dimensionless, right?
No, dimensionless.
So it's the over density as you define it. The density divided by some comparison density.
Yeah.
So if you go to the next page.
That's good. 20, yeah.
Yes. So it's also something related to a comment by Raphael, because one of the advantages of using, sorry, it's a police car passing by.
Okay.
So about the symmetry of the clusters, maybe somehow if you explore again this the same simulations, maybe something that could be done here would be to characterize these asymmetries with maybe the standard deviation, these profiles.
Actually, I kind of did. I should have shown that at that time. But here I got it for like...
Yeah, because it illustrates well the asymmetry, but maybe you could characterize it statistically from what the simulation gives about this. So it would be a stronger argument that the simulations show such a level of asymmetry, and you could put, for example, using the standard deviation or the spreading in the profile. Right? Does it make sense?
Mm-hmm. Yeah. Can you repeat the last comment?
Yeah. Just some way to characterize. Maybe you can find some way to extract from the simulation you are using.
Mm-hmm.
The asymmetry of the clusters.
Okay.
Because it's as you mentioned along the text, they can be an important component to give your results.
Mm-hmm.
And yes, and something I found interesting, if you check in the profiles of the dark matter and the gas, is that they do not follow each other for different redshifts.
What do you mean that they do not follow?
Yes, for example, the lower curve is for the highest redshift, is the magenta curve, in both cases, in gas and dark matter. But when you go to smaller redshifts, so they do not follow the same trends. Is it so?
Okay, in the okay, up to redshift like 0.9 or below, like 0.5, you find like massive clusters, but like even 10 to the power like 14.8 or something like that. So, but above that you don't. Okay, so okay, because okay, so we have a whole simulation. So I choose the most massive clusters, one for different at like the maximum redshift, or at the redshift I'm showing. So that's why you can say, okay, I do find a massive cluster at that redshift.
Mm-hmm.
So, and
right.
Okay, their mass is kind of increasing.
I see. Mm-hmm. But the redshifts. Okay, I understood you took 5 clusters from your simulation. Is it so?
No. Okay.
For doing these curves.
So these simulation. So I took 4 clusters, from a simulation at different redshifts. So we have snapshots. So at redshift like 0.1, 0.01. So we have a whole population of clusters. So I took one cluster from that, and then from another snapshot, then from another snapshot. So you are commenting that at the high redshift, there should not be that massive cluster. Yes.
I think it's. I can understand why the profiles of the gas and dark matter, they do not follow each other. They do not go up and down following the redshift. But maybe is it like this?
No,
it's a behavior not very easy to understand.
Yeah, and because so there are different so in the cluster. So usually there is it's a sum of dark matter mass and the luminous mass. So in this cluster, so I would find that more like in green curve, there will be more dark matter particle than the baryonic particles. So
yeah. Can it be due to the choice of the cluster, the specific?
Yeah,
it's some sampling effects.
Yeah.
Okay. Thank you. So if you go to page 23.
On the PDF, yeah.
Yes. So this first plot. Maybe, do you think, maybe you thought about this, I don't know if it's interesting, could you try to derive a different, because you have this analytical profile, right, this orange curve, this,
yes,
you show the formula, and you have I think this is an average from the simulations, this blue curve.
Yeah.
Maybe do you think would it be useful try to fit analytical curve? Maybe it would be useful for doing simpler works in the future using this profile derived from simulations, and that we guess are more precise than this orange one.
No, I don't understand your comment. What's your question?
Yes, do you think it would be interesting try to derive a new analytical profile fitting this curve that you extract from the MATD simulations? Because it's much simpler to deal with, make some estimatives and calculations. If you have some analytical profile, it can be useful, don't you think?
Yeah, okay. In case of analytical, it is simpler. You don't need a background MATD simulation. But then on the other hand, you are not considering the more realistic background, the density distribution or magnetic field, if you're considering analytically. So that's why we did that main detailed analysis. So if
I see. No, I'm not questioning why you did, but I'm telling you maybe it's another product you can extract from your data.
To exactly fit the analytical profile?
Yes, because if this difference
is not that much
in the outskirts of the cluster.
Can I interrupt, Saqib? What Reinaldo is saying is that it may be useful in the future to have this profile and analytical expression for the simulated profile, because it provides a correction in the outer parts of the cluster that is not in the beta model.
Okay.
It's simply a suggestion.
Yes, it can be used for theoretical people. They do not deal with simulations, so they can take your profile and plug in their models.
Yes, that can be done, but it will be different for each redshift. Or
I see.
Yeah, you can do that. So, okay, for each redshift, for each mass range, you can do, because you can plot analytical profile for any mass range, and then you can have the same profile from the like MHD, and then you can create actually the formula. Yeah.
Right. And also this lower plot was already discussed by Kohta, right? And this distribution, differential distribution. So my question is, because I see the behavior of the curves following the redshift, they're also not very easy to understand, because sometimes you have a reduction in the number of clusters of the lower masses, but then they increase again. Do you think, because I understand from the text, you did not use all your sample of clusters. You took a subsample of your simulations to make this count.
Yeah.
Did you check if the error, the standard deviation of the error in this curve that you extract is small enough? Maybe it was necessary to take more clusters from your simulation to make this count, to make it statistically more precise? Because you do not show us the errors here, right?
Yeah, it didn't show. Okay, so as Kohta also suggested that to improve or at least compare with the observation, so that you can see like what's the main difference between the mass function you are using and in the literature. And yes, so but I would say like the sample I use from the background simulation, I almost explore like you can say 1/4 of the part of the whole volume. So and then okay, you're suggesting even more, but at some point I haven't showed that, but I did calculate the standard deviation, and it was not can say very pronounced, or which can be noticed or something.
Right. I saw the text. You took 20 subsamples of 20 megaparsecs to cube.
No,
so
it's like okay, it will be, and it's in each direction as well. So
okay.
Then you can.
So you say you took almost a representative part of the simulation, not as small. Oh, okay. So okay. Thank you. Okay, going on. So you are making the propagation of cosmic rays. So in the assumed turbulent magnetic fields in this environment. So I guess this magnetic field, I don't know if this turbulent part of the magnetic field appears in the simulations, because we are always constrained by the resolution, right?
Mm-hmm.
So does it appear clearly, this random part of magnetic fields?
No, actually, so the resolution, the maximum resolution we get in the center, or you can the best resolution, is like 10 kiloparsec, and away it's even 50 kiloparsec.
So it's a good resolution.
So
10 kiloparsecs.
Only in the center, but as like you can say within 100 kiloparsec. Above that, it's even 30 or 50.
Right. And I have one curiosity. It's out of the scope of the work, but did you check? Maybe you can check if you did not. How much of the magnetic field amplification is due to only compression? Because looking to the profiles of the magnetic field, the density, it seems very clear. The magnetic energy follows very well the density.
Yeah.
So how much comes from turbulent amplification, and how much is just due to the compression of material? Maybe you could take a look. I think it's also some interesting information, and also to see how much of this random component you could get from your simulation, right?
Yeah, because this can be done. So you can focus like on you can say a very small volume, like say 10 megaparsec or even lower, and focus on one source and then study these, I would say, microscopic parameters. Okay, so like magnetic field turbulence and like the detailed analysis of the background environment. So right now you can say our simulation volume was just too big, and we didn't focus on that yet.
Yes, but even so, looking to your profiles of magnetic fields and density, they follow very well. the
Yeah, there
square
are-
of magnetic field is almost identical to the density.
Yeah.
So it's it seems at first sight, probably it's an effect of averaging, that the simulation cannot produce too much amplification due to random magnetic fields, because it has implications, because you are using this magnetic field from the simulations to propagate cosmic rays,
Yeah.
right? So the topology maybe will affect how the cosmic rays will be trapped, how they propagate, and if the simulation cannot resolve this random component, maybe it's some case you have to add by hand some additional some reduction of the diffusion coefficient of the cosmic rays, because from the simulations, if you don't have these random components, maybe they will diffuse much more effectively than if you had these random components that would trap for more time the cosmic rays and maybe would produce more neutrinos and gamma rays.
Mm-hmm.
Does it make sense what I'm saying?
Yes, but I will again say, so we can do that advancement as well.
Yeah,
like
it's just something for the future. It's
Yeah.
I think that's it's necessary to do. Yeah.
Can I make a comment on that? Yes, Reinaldo, you are correct, and this is one of the issues to explore in future work. One of the things that we want to explore, as you may know, and actually there is a study by Vaza and others where they try to reschedule these magnetic fields in order to separate the compression component, or the magnetic field increase due to compression, and also to dynamo amplification. So they rescaled out of anybody's simulations. They rescaled and tried to include these effects by hand, right, in order to see how cosmic rays would propagate and the feedback on the magnetic field distribution as well. So this is a study that we can improve their study actually, because we
extension.
Exactly. So this is one of the issues, for instance, that we can explore, in the continuation of the works with the Stellinha and even with Saqib. Just that Saqib probably will move a little bit subject, but yes, definitely.
I will collaborate.
This is yes. This is doable, and it's one of the steps in exploring cosmic ray diffusion in a second order effects that may be first order effects actually, right?
Yeah. Thank you. So Saqib, when you describe the methodology for the cosmic ray propagation, I understood from the text that you solve the transport equation, right? The diffusion equation, instead of doing test particles. Is it so? And you solve the diffusion equation also for right. Okay, so you have to assume this diffusion coefficients. So it was already discussed a little bit about the anisotropy of this diffusion coefficients. I would point you to take a look in this in a specific section of propagation of cosmic rays, where you describe the methodology. Is 3.1.1, because sometimes the reader can understand that you are using test particles. Because, for example, when you define the observer, you say you take the information when the particle reaches the observer, or when the energy of the particle becomes smaller than a given minimum energy, but instead you are solving the function that describes the density of cosmic rays. You are not following individual particles, right? So take a look again. Maybe some parts are not necessary that are devoted to, because I know you made experiments also using test particles, but I think here these main results, you solved the differential equation, right?
Yes.
So just to make it clear for the reader, so it's more pedagogical. Yes, for example, the energy loss algorithm, see if this is still valid with this methodology you are using. Okay, I would, yes, someone already complained that some things are mixed, some interaction, pair production by the interaction of cosmic rays with photon fields, and the absorption of photons by interaction photon-photon. So they are mixed in one section here. And also, maybe I understand why you showed this figure of the air shower to so that figure that shows the primary gamma ray entering the atmosphere, but you were using this in the context of the interactions of particles in the cluster, right? I understood that it's just an example, but it's maybe you can find for example, you are discussing the absorption of photons by interactions of photons, production of by the photon-photon interaction. But here, when you have the air shower, you have the other interaction, the interaction of the gamma photon with the nucleus in the atmosphere to produce the pair. So maybe this figure is not a good choice for what you are explaining.
Okay.
Take a look again. Yes.
You mean because atmosphere? Because atmosphere could be the background, actually. It's the background.
Yes, but exactly when he talks about the interaction photon, the pair production by the photon absorption.
Yes.
So he shows this figure. So in that place is not a good choice. This, but I understood it was just an illustration. Yeah. So I think this chapter 3 is the one that you can use this suggestion by Gastão to make it more pedagogical. Maybe some sections you could just break in sections, divide the first interactions of I don't know, the interactions of gamma rays propagating the medium and interactions of the cosmic rays. Maybe you just separate them, would be clearer for the reader. And okay, let me follow. Okay, so if you go please to the page 55. Yes. So you show the cosmic ray spectrum. I think after you propagate a little bit, when you use different anisotropies in the diffusion coefficient. So the difference, fortunately, is not that large. It must be a factor of 2 or 3 for the smallest energies you are considering. Because, okay, I understand you're considering propagation of cosmic rays over scales of megaparsecs, right?
Yes.
So over these scales, why not to consider the diffusion isotropic? Because you are above the scale of turbulence, and the turbulence is super alphavenic. It means that it can make a random component very isotropic of the magnetic fields. So why do you consider anisotropic diffusion coefficients?
Because, okay, so we took it, okay, as it's more according to literature as well, and I think it's more suitable for the intercluster medium plasma because the magnetic field, the parallel diffusion coefficient is bigger than the perpendicular. So
yes, it's true, but you are considering diffusion over scales where the magnetic field doesn't have a preferred direction, because it's, I think you are assuming it's turbulent. I don't know if it's, if the simulation can show this, but you mentioned the text, you are considering Ma alpha-Venic number, which is the parameter that says that the field is more or less isotropic over at least scales larger than the turbulence scale. So I don't see a strong justification why to use this anisotropy, but it seems, looking to these curves, it
doesn't make any.
It changes a small amount. It would be much simpler just to use an isotropic for those scales. Maybe I'm wrong, but this is how I see this if you invoke that the scenario is turbulent.
Can I make a comment on this? Yes, Reinaldo, in principle, yes, but you have to integrate these particles over several orders of magnitude in distance, from kiloparsec to megaparsec scales. And also you have to take into account that it's a large energy range of particles, from lower energy to very high energies. So it's, I mean, it's a more conservative approach if you take into account this anisotropy, regardless of the fact that it might be smaller as you integrate over distances. But yes, this is one of the issues, you know, this
yes, I think this is polemic.
Yeah.
I will not agree that it's more conservative, but I understand a lot of people do this, but over the scales you are considering, you don't have, let's say, a preferred direction of the magnetic field. And if I understand what's happening here, you, I don't know if this is the case. It's mentioned in the text, I think it's out of context, but that this diffusion of the magnetic field is not due to resonant interaction with waves, but due to the, let's say, to the magnetic field diffusion, the field lines diffusion. Because I understand that the Larmor radius here are too small, right? Even for the highest energies you are considering here, 10 to 17, 10 to 18, are still kiloparsecs, below kiloparsecs, right? And yes, and yes, I don't see too much justification. And so there is one affirmation here about this diffusion coefficient that relates to subalpha-Venic turbulence. This anisotropy going with the Ma alpha-Venic number to the power of 4. So this is not the case here, because it's clearly stated that it's subalpha-Venic, right? So it can be corrected in the same page, in the paragraph below this figure. So it's right. This this discussion about the perpendicular diffusion coefficient, blah blah blah. So this is effect of subalpha-Venic turbulence. So I think it doesn't apply here, because mostly it's superalpha-Venic, right?
But it is true for the intercluster medium, yes? But it's true for
no,
the medium, yeah.
No. What I'm saying is that this law, this detail about the anisotropy and the diffusion coefficient, it's for subalfvénic turbulence when the magnetic field is much stronger compared to the motions. So they are not too much deformed. So the particles, they can flow more easily along the field lines and not perpendicular, as you correctly said. But your case is that your field lines are packed. Yes. So this information you can clarify later on. So there is at the end of this chapter. So there is an you say that okay, I understood you use only protons in this study and not nuclei, but the justification I do not understand quite well. I think Rafael mentioned this. I think he understood, but I didn't. In the last paragraph of this page 56, so you have also the Larmor radius of heavy nuclei is comparatively smaller than of protons. Is it not the opposite if they have the same energy?
No, it's not the opposite. It's because you divide it's by the mass number. Yeah.
No, you have a heavier particle and a lighter particle. If they have the same energy, which one has the larger Larmor radius?
I will show you the formula.
The bigger Larmor radius. So think an electron and
it's like this. So
okay. So I hadn't understood. So okay. So considering particles with the same energy.
Yeah. So you have a smaller.
Okay. I think I still do not understand exactly, but yes, if you're saying, I think it's correct. Because the mass will be the charge will multiply by z, but the mass will be with like 2z, right? Later on, I will check to understand this. It's some doubt I had. Okay. And going to the next chapter. I think I had the same doubt that Ulisses about that plot. Oh no, the next chapter.
Reinaldo, sorry. Your doubt was with the mass relation, the mass dependence.
Yes, in fact, the Larmor radius for protons and heavier nuclei. So the heavier nuclei have a smaller Larmor radius. This is what Saqib was explaining.
Yeah, because there is this z in the denominator, right?
Right. Yeah, this is something I was in doubt. So chapter 4 and chapter 5, I think I have the same doubt as Ulisses. I would like to ask about this flat behavior in our curve of the spectrum of the gamma flux, but it was well discussed here. And by the last, it's just a comment about one statement in the conclusion. If you go to page 99. So This paragraph starting with cosmic ray acceleration galaxies. So in the middle of this paragraph, after these citations, cosmic rays are present in galaxies and clusters with an approximate partition to the thermal turbulent gas and the magnetic energy densities. So if you understand the meaning for this statement, is that the energy of density energy of cosmic rays are in close partition to the other non-thermal components in the cluster, but I think for the cluster this is not true. I have some number in my mind here. It's about 6%, so it's dynamically not very important in cluster environment. The cosmic rays, so the energy density is much lower than the other components. The thermal is much higher than the magnetic, also in clusters. So what you are saying is true for galaxies, but not for clusters. So
but
something.
I think it's like I saw at least in the Nishiwaki paper they calculate the energy density of cosmic rays over thermal energy density, and it was increasing toward the outskirt. So
to the point to be dynamically important.
It was the number, as far as I remember, it was like 10 to the power -2 or even something like that. It was
Yes,
Brunetti who
yes,
estimated.
Brunetti has some review about this, but the number I have in my mind is like you said, 10 to -2 is 5%.
Oh, so it's like, so you are saying it's dynamically not important. Like,
I can be wrong. I don't know if someone has fresher information in mind, but the number I have in my mind is this. You could check in some review.
Yeah, I think that this number is usually not so important. Although some people still think about the possibilities that density is higher at the outskirts. But we don't calculate, right? So the Brunetti and Nishiwaki, basically they actually treat the cosmic ray distribution, this ratio, non-summer to summer pressure, as a parameter, kind of an arbitrary parameter, and they try to adjust this distribution to explain the radio data. So in this sense, I think that in principle, this quantity should be determined by the calculation. In this case, I think that ideally is, I think that performers, these groups are doing, it's kind of probably interesting to do some simulations, taking into account the possible feedback by cosmic rays, right? And this could be, yes, usually, typically, we expect that the ratio is small and not so important, but might affect some, might be some effects in the outskirts, maybe.
Perhaps. Yeah, I think this is still an open question. So yeah, definitely.
Right. Well, thank you to everyone. Congratulations again, Saqib and Betty, for this huge work. I think congratulations, especially for the results. I think they are very relevant and interesting for people in the field. That's it.
Well, thanks, Reinaldo, for your feedback. Your comments are certainly very important and will be taken into account. And as some of them are already being taken into account. I would like to thank all of you, but I should say a few words, because I'm not going to question Saqib anymore, because I have questioned over the last four years, right? So what I might say is that Saqib, when he arrived in Brazil, he had a very busy and hard time in the beginning to get used to keep up with the rhythm of I mean, to get familiar with the our own way of living, of exploring, doing research, and the courses as well. And so in the beginning was really hard for him, but he overcome could overcome all the difficulties, and I might say that he has done a very good work, considering all the, because we are combining different techniques, different approaches, different fundamental issues from magnetohydrodynamics in a cosmological environment, and non-thermal radiative losses in high and low energy, all these processes combining with the thermal process, understanding all these processes and cascading, dealing with these different tools from cosmological simulations, regardless of the fact that he did not produce these simulations. It was rather important for him to understand what these simulations were providing, to understand how these simulations are performed, to understand magnetohydrodynamics. So all these issues he could overcome, he could keep up with, and then he could produce these integrated diffuse contribution from clusters with this combination of these techniques, and using Monte Carlo code as well.
Your mic is muted, Elisabete.
Oh my God! Sorry.
The last 10 seconds.
Okay. So I think it was accidentally that I pushed the button. But anyway, so Saqib were able to combine these different techniques and understand, more importantly, understand how to use all these different approaches and to do his best. So I think he has accomplished the main purposes of a PhD work, and the results by themselves are very interesting and new. And of course, we have this flatness in the gamma ray distribution that it was quite a surprise, and we are still exploring the origin of this flatness, and checking whether it is reliable. We believe so, based on the techniques and on the tests that we have performed. But there are still some issues that we can explore better, as suggested, for instance, by several of you, and Kohta in particular, with regard to the cluster mass function distribution that we extract from the simulations. We would rather, yes, explore more this issue, and cosmic ray propagation as well. All the assumptions that we made towards cosmic ray propagation, in general, they are quite standard-like. So I wouldn't say that we might identify any problems here, but there is still issues to be explored, very important issues towards this, for instance, as pointed out by Reinaldo on isotropy. But on the other hand, this small anisotropy effect that we considered will not impact too much on the results. But anyways, cosmic ray diffusion in these systems, propagation and acceleration and reacceleration, are still major issues to be understood in these environments. And what else? I mean, the comparison with the sensitive curves of the instruments, yes, we were aware, of course, that these sensitivity curves were made for individual sources, even though we tried to take into account the extended effects or corrections that were provided by some of these experiments. We are aware that these curves are just to give a guide, to guide our eyes, or the eyes of theoreticians and observers. But I think these aspects should be, let's say, more explored in the thesis as well, right? Because of course it's not up to us to evaluate the sensitive curves of these experiments, but at least we can provide some suggestions on how to predict or how to make this comparison more clearly established. And so I think I should congratulate Saqib for what he could surpass, because this was really a challenging subject, and I think he could accomplish, of course, with a lot of help from Rafael Alves Batista, who is here, who was one of the writers of the CR-Propa code for doing cosmic ray propagation in the Monte Carlos in the cascading to get all the emissions, all the byproducts of the cosmic rays. So his help when we started this project, Rafael was working with us as a postdoc in my group as well, and so this collaboration was very, very fruitful, and it's still going on. So, and again, I would like to thank all of you guys, all the examiners for your participation. And now it's time for us to get together in another room and discuss about the work of Saqib and decide about his defense, right? So I would like to invite you for us to change to this other room. Richard, can I ask you? I only have to push the button for this.
Yes, just to push the button to participate.
And all of us, I mean the bench, not you, Saqib, we should go there. Is that so? And
yes.
then we come back to this room when we have made up our minds, right? We have decided about, right, when we have a result. Is that correct, Richard?
Correct.
Okay, so does everybody see this participar?
Right?
This, yes. All of you, Kohta and
Yes.
the others. I'm asking Kohta because, yeah, so you should push participar, which means participate, and then we move to the other room.
Oh, let it be. Ah, tá. Tá bom.
Aí aparece quem estiver falando.
Yeah, good. Yeah. So normal.
Eles me deram defesa de doutorado, vocês vão atrás de meia hora, sim, até foi curto por ser o meu microfone está aberto. Agora que eu vi.
I cannot hear you, Betty.
Microphone is mute, Elisabete.
Sorry. So, Saqib, the board has concluded that your work deserves to be approved.
Mm-hmm.
So you are a PhD. Congratulations!
Thank you, everyone.
You've got your PhD.
Congratulations.
Thank you, everyone.
Congratulations. And just that the board asks, of course, that you should take into account those suggestions that they made for the monography, right?
Yeah. Mm-hmm.
So you are going to include these changes in the monography, and then you will have some time according to the program to present to this final version that should be issued not only to the members but it should be published, right? After these modifications. But congratulations, Saqib, and yes, and I wish you all the success in your postdoc in Gran Sasso, right? Italy, with the neutrino experiment. And of course, I hope that we continue with this collaboration, because there are several avenues that you opened with this work, that we opened, and we are going to continue to explore, second order effects, and some of them that may be first order effects. Again, I'd like to thank all the members of the board. Thanks a lot for your patience, for your time, and especially to Kohta, because I know you are in a different time. There is this time lag, and you have commitments right now, and we are a little bit late. We ran out of time because of the confusion with the Klaus in the beginning. So again, thanks a lot to all of you. And if you wanna leave right now because you need to leave, you may leave. And of course, if you guys can stay for a while, we can talk without recording anymore, because I think now it's time to finish the recording, and
Okay, I'm going to stop the recording here and stop the YouTube transmission. Just some seconds.
Okay.
Okay, so thank you very much, and probably I have to go soon, so that because I have actually to be charged of this.
Okay, so thanks, Kohta Murase, for very beautiful comments and really good comments. So
yeah, if you have any questions, let me know. So keep in touch.
Okay, thank you.
I already sent some references which could be useful. You can check later.
Thank you.
Okay, bye. So
Bye.
Saqib, if there is some people on YouTube, if you wanted to thank someone of your family, someone that is watching, the moment is now. I'm going to close it.
None of the family member is watching, so don't worry.
Okay.
Okay. So Saqib, yes. Now we are not recording anymore, so you can relax and enjoy.